Welcome to the second round of talks of the CM3 parallel session. As you can see, as I have shown before, the time schedule is quite tight today as well. So it would be very nice if all the speakers should respect the allocated times. In any case, I will warn you 3 minutes and 1 minute before the end of your talk. So on Monday, everything went smooth, and I hope today it does as well. Professor Mavromatos, if you want to share your screen just to be ready and start on time. Okay.
Yeah, you can see my screen,
yes.
I suppose.
Yes. So let's wait 1 more minute.
Yeah, please let me know.
Okay. Okay, our first speaker today will be Professor Nick Mavromatos from King's College London, and he will talk about gravitational anomalies, actions, and a string-inspired running vacuum model in cosmology. Thanks a lot, Nick.
Thank you very much for the invitation. So my motivation is the standard one. Lambda-CDM works very well at large scales. Also, general relativity of Einstein, including the recently discovered gravitational waves and black hole photographs, works perfectly. I mean, almost perfectly. But there is the need to go beyond because of various reasons, some of which I stated here. We don't understand anything on the nature of the dark sector of the universe. We don't know, we don't have a complete understanding of inflation, in the sense that we don't know whether inflation is due to a fundamental inflaton field or some underlying nonlinear dynamics, as in the phenomenologically successful Starobinsky model. Moreover, of interest to this session, we have a lot of recent hints that maybe we have to go beyond lambda-CDM because of the tensions between the lambda-CDM and local measurements of the Hubble parameter, and also the so-called sigma-8 tension in the galactic growth, galaxy growth data. Of course, leaving aside the theoretical motivation that, for instance, general relativity is not a normalizable theory of quantum gravity, I would like to add one more thing here associated with which usually is an issue which is in the realm of particle physics, namely the current lack of a microscopic understanding of matter-antimatter asymmetry in the universe. Zakharov has actually attempted to solve this problem by postulating his famous condition, which mainly states that CP violation plays an important role in generating baryon asymmetry. And of course, in the standard model, you need to go beyond the standard model to resolve this issue, because the amount of CP violation in the hadron sector of the standard model, as observed so far, falls several orders of magnitude below the required amount to explain baryon asymmetry in the universe. A basic assumption is CPT conservation, which Zakharov has made. In this talk, I would also attempt to go beyond that, claiming that there may be some CPT violating geometries in the early universe. Let me give the overview, which will be the bulk of my talk, which consists of a description of the parts and the whole. These are two intertwine and tangle issues, paraphrasing the famous the part and the whole of Heisenberg when he was talking about quantum mechanics. Here I'm going to talk about quantum gravity in a sense. So I will argue in this talk that deviations from lambda-CDM and alleviation of cosmological data tension in the current era, plus observed matter-antimatter asymmetry, can be linked with microscopic string-inspired models of cosmology, hence going beyond general relativity, which are plagued with gravitational anomalies. In such models, I will link this with primordial gravitational waves and induce spontaneous Lorentz and CPT violation as a result of anomalous condensates, plus a geometric torsion interpretation of dark matter, which is due to some kind of actions which appear in string theory. So here are the parts, and this is the whole, namely a string extension of the running vacuum model. And now let me discuss, due to lack of time, only part of these parts. including the Hall. So let me start with the Hall, which is a framework that has been presented in yesterday's session by Jean Sola. What is the running vacuum model? Is a cosmological model in which the vacuum equation of state is that of de Sitter, but the energy density is not constant, depends on time through even powers dependence of the Hubble parameter, which are dictated by general covariance. Actually, for the entire phenomenology of the universe, truncating this series to fourth power suffices. And it is important to notice that the evolution of this vacuum obeys a renormalization group-like equation of state, where the scale of the renormalization group scale role is played by the logarithm of the Hubble parameter. This evolution is based on conservation of the stress tensor of the theory, and in fact, it can lead to an early de Sitter unstable phase in the universe, where the h to the fourth term in the energy density plays a role and dominates. And then eventually you come down to in a smooth way, because in the standard RVM model, these coefficients are assumed the same. And you come down to the current era, where you obtain, as a result of the coefficient of the h square term, mu, you obtain deviations from the lambda CDM. You see here, this is not the standard matter, but you get this correction. And this, you have heard talks in this session about this. This could alleviate the tensions. I will concentrate for the purposes of my talk on this type 2 RVM, which contains logarithmic dependence on the Hubble parameter. And in particular, in this talk, I will obtain a type 2 RVM from gravitational anomalies in string-inspired cosmologies. We have recent works with Joan Sola on this, and this work is based also in collaboration with, partly with Spiros Vassilakos. So let me start by describing the various parts by this first explaining what gravitational actions are and what which will play a crucial role, and what is their connection with torsion. In the massless gravitational multiplet of string theory, which is also the ground state of string theory, if in case of superstrings, you obtain, you have, in addition to the scalar, which is the dilaton, and the spin 2 symmetric tensor, which is the graviton, a spin 1 antisymmetric grand tensor, the so-called Kalb-Ramond field, which is actually the action, the so-called model-independent action. You have many more actions in string theory arising from compactification. In 4 dimensions, this action appears in the gravitational part of the action only through its field strength, which, by the way, is no longer given, is not given only by the kernel of beta, but is augmented by Green-Schwarz anomaly counter terms, Chern-Simons terms. Omega is the gravitational spin connection, and A is the gauge field connection, because these are required to cancel anomalies between gauge and gravitational sectors in the extra-dimensional sector of the string. In 4 dimensions, we are going to maintain gravitational anomalies in this talk in a self-consistent way. The torsion interpretation of this field H comes about because when you combine the H square terms with the Einstein-Hilbert term in the action, you can write this action in terms of a generalized curvature, which, in view of the total antisymmetry in the Lorentz indices of the H mu nu rho field, this connection is not symmetric in the lower indices, and this field plays the role of torsion. I will assume the dilaton throughout as constant in throughout this talk. When you integrate out in a path integral the H field, you have you implement a Bianchi identity as a result of the definition of the field strength. When you act with the derivative here, you get the derivative of these Chern-Simons terms, produce the anomalies. The tilde is the dual, and then you implement this Bianchi constraint through a pseudo-scalar Lagrange multiplier, which plays the role of the action, and this is your gravitational part of the action. The action couples to the anomaly terms, and also its derivative through its derivative to the axial fermion current if you have fermions. Both of these couplings are CP violating. Classically, the duality means that the derivative of the action is given as the kernel of this torsion part of this field strength. This term is 0 for Robertson-Walker backgrounds, and therefore the action and the whole model, which will describe the dynamics, the gravitational dynamics, is this, plus you have the fermions from the standard model, which could be Dirac or Majorana, plus the gauge fields, of course, all the other standard model sector when it appears. Let me discuss first the role of these anomaly terms and why the gravitational anomalies contribute to the stress tensor, which is important. Anomalies, as you know, arise from triangular graphs in 4 dimensions. In a d-dimensional graph is d half plus 1, through the circulation of chiral fermions. I'm going to concentrate on this part, which couples actions with gauge of gravitons. Anomalies, if they are present, lead to the breakdown of the chiral axial fermionic current. And these terms, the duals, are defined in this way in 4 dimensions. Unlike the gauge field, the term in the anomalies, which is topological and does not contribute to the stress tensor, the gravitational part does, because when you vary this with respect to the metric, you get the so-called cotton tensor, which is given here and is proportional to the derivative of the action. Notice that if the action is constant, this term is total derivative, so there is no contribution to the stress tensor for constant actions. The cotton tensor is traceless, and it has the important property that it contributes the negative contributions to the stress energy tensor, as we shall discuss later on. In the presence of the cotton tensor, if you have matter, the stress energy tensor of matter, which in this case includes our gravitational actions, is not conserved because of this divergence property of the cotton tensor, which is proportional to the anomaly. This, however, does not mean any bad thing about the ferromosis breaking, because you can always define an improved tensor, and this part simply describes the exchange of energy between the actions and the cotton and the actions and the gravitational anomalies. And now our action is in the gravitational multiple. Let me discuss now primordial gravitational waves and their importance. First of all, a very basic important assumption in our cosmology is that in the very early universe, the only external degrees of freedom are bosonic. Fermions come at the end of inflation. These bosonic degrees of freedom with constant dilaton is only the action and the gravitons. If you don't have gravitational anomalies, the system consists of stiff matter with equation of state W equals +1, because there is no potential for this action. Zeldovich had a stiff matter model in the very early universe, but in his case, stiff matter were associated with baryons. In our case, they're associated with action. Savanish have also discussed from a different perspective than ours, stiff matter in early universes. Potential origins of gravitational waves in a pre-inflationary era has been discussed in our review with Joan. And here I concentrate on one origin, which is actually associated, which is actually fitting our assumption that only gravitational degrees of freedom are present. Namely, I will discuss supergravity models, and the gravitational waves in such models arise from non-spherically symmetric collapse or collisions of domain walls. The latter are due to the presence of an approximate discrete symmetry breaking, with the discrete symmetry breaking being associated with a bias in a condensate of gravitinos, say. A bias in double well potentials of this condensate. I will consider the gravitinos. This is the gravitino condensate. There is a statistical bias related to different occupation probabilities between the two vacua due to percolation effects, as discussed by these people. And there are imaginary parts in this effective potential. You can compute them. There's a finite lifetime in first hilltop inflation, which is not necessarily slow roll. And then the system tunnels through this stable vacuum where supergravity is broken. The gravitino is massive, with masses up to Planck scale. And eventually, the gravitational waves condense and lead to the RVM vacuum, as we are going to discuss soon. Therefore, we have in our model two inflations, which are being interpolated by a stiff matter Karl-Bramon action dominant era. The first inflation ensures that spatial inhomogeneity are washed out before the RVM inflation. Let me now explain how Lorentz sensitivity violation from anomaly condensates arises. This term, the anomaly terms are non-trivial if gravitational wave perturbations, i.e. CP violating perturbations, are present. And these Chern-Simons terms can be split into a condensate part and a quantum order part. The condensate part behaves, as we shall argue now, as a cosmological constant, slowly varying the Sitter type term in the action. How you do that? First of all, you assume a de Sitter era so as to be able to estimate the condensate of gravitational degrees of freedom of gravitons. Then you deduce an RVM vacuum. You discuss the equation of state. You show that the energy density has the RVM form. And then you use this RVM form to obtain self-consistently inflation that you assumed before from the RVM evolution, as I discussed before. The condensate is computed by introducing metric fluctuations which violate CP here, and these are the linear gravity. This is linear quantum gravity computations. This is the condensate. That's the anomaly. You assume homogeneity in isotropy here, which is guaranteed in our case by the first inflation. You assume a slow roll axion field, so each time derivative is very small, so you do the computation to first order, and then you arrive at this equation of motion for the time derivative of the axion field, which is proportional to the temporal of the anomaly current. I remember I remind you dm km is the anomaly, and then this is the equation for the anomaly, which in general is washed out exponentially unless there is a specific relation between the ultraviolet cutoff that you introduce for the graviton modes and the string scale. This value you take from the Planck data, which is of order 10⁻⁵ if you want phenomenology. Then you ensure with this assumption constant anomaly, and because constant anomaly implies constant temporal component, that's enough in the homogeneous situation, and because the constant anomaly implies b dot equals constant, that translates to a constant field strength, which in fact is a Lorentz violating solution, NCPT, because you violate Lorentz, you violate CPT. There are no Transplanckian modes, and when you combine this assumption with the slow roll assumption for the Carl-Ramon action, you restrict the string scale to almost 10⁻⁵ and Planck in this model. Now let me discuss how inflation goes. You have this almost constant rate of change of the Carl-Ramon until the end of inflation. You evaluate this means that there is a linear time dependent until the end. Taking into account that the end of inflation gives the number of refolding, you can actually arrange so as the initial B, which actually turns out to be bigger than the M-Planck, but there is no problem with Transplanckian modes because the effective action depends only on the rate of change of B dot, and that's subplanckian. And you can arrange with this in such a way so as the condensate this to be approximately constant, and then you obtain all the contributions to the total energy density from the axion, Chern-Simons quantum terms, and the condensate. And you see that this has the even power dependence in the Hubble parameter, which is of RVM type, and actually h to the fourth in this case. There is an equation of state where it not for the lambda term, you observe that there is a de Sitter type equation of state, but with a negative energy density. That is phantom matter, as you can see here, between P and rho, and phantom matter has been discussed in earlier works by Joan Solat, independently of the present context. If, however, there is a condensate and there is simultaneously with phantom matter, you see that the system switches to a standard de Sitter true RVM vacuum with a positive energy density because the lambda term dominates. So these terms drive inflation in the way I explained before. They are associated, they are dominant in the early universe, and in our case, they cannot be reproduced by quantum field theory contributions, but are due to CP violating couplings of gravitational actions with gravitational anomaly condensate.
Nick, 3 minutes.
Oh yeah, that's fine. And then you have another important role of CP violation in the early universe in a different context than Zakharov. There is a comment that the coefficient of H squared term is negative in this particular case, unlike in the late era, but after we exit inflation, this can become positive due to contributions of cosmic field. The slow roll for this inflation is, there is no inflaton here, this is dynamical, but the slow roll is placed by the epsilon field. So there is an undiluted Carl-Ramon action at the end of inflation, which is important for leptogenesis in the following sense. So far, you had only gravitational degrees of freedom. At the end of inflation, you have fermion chiral matter generated, and then you have cancel the chiral matter generates gravitational anomalies which cancel the primordial anomalies, and then you have chiral anomalies which remain only, which are responsible in the matter era for giving masses to the Carl-Ramon action, and therefore this can play the role of dark matter. There is leptogenesis through baryogenesis in this case, which now I described in my last transparency as by giving you the summary. So you see, you have gravitational waves from a pre-inflationary phase. These lead to anomalies. They lead to an undiluted constant Carl-Ramon axial background, and the latter communicates to leptogenesis because after the cancellation of chiral anomalies, after the cancellation of gravitational anomalies, this background still remains in the radiation era, and in theories with right-handed fermions, decays of right-handed fermions in this background can produce lepton numbers, which then are communicated to baryon sector by B minus L number, by B minus L conserving processes. Finally, in the chiral, in the matter era, chiral anomalies which remain through instances give masses to the Kalb-Raman action, which can play the role of dark matter. I don't have the time to discuss this coincidence problem in today's era. You can match it and thermally and match it with the inflationary era, and you observe that in order of magnitude, the slow roll
1 minute, Nick.
Yeah.
Sorry.
Yeah, fine. So I finished with this current era, which is RVM inflation, could alleviate the tension. And for us, the type 2b comes from integrating out gravity on degrees of freedom, but the cosmological constant remains constant. So to conclude, I will give you the basic cosmic cycle, the string RVM, and I want you to take the message that we exist because of gravitational anomalies. I had some outlook for actions, look for the CPT violation, and look probably for this negative term, but I will not have time to discuss it. I thank you for your attention, and I leave you with some references here. Thanks very much.
Okay, thank you very much, Nick, for this very interesting talk. Now it's time for questions. If there is any, please raise your virtual hand. Okay.
Well,
okay, yeah.
Well,
Yes,
I
please,
think, yeah, thank you, Nick, for the nice talk. I think that not everybody is acquainted with what phantom matter is, so perhaps you want to explain.
Yes. Phantom matter is actually, let me go back to the transparency. If you have in a P row, if you have a pressure and energy here, if you have a system with an energy density which is negative and pressure which is positive, so you have in this regime, because the pressure is positive, this behaves like matter in a sense, but it's phantom in the sense that its energy density is negative. So that's not normal matter. It's not phantom energy. Phantom energy is the opposite situation. You have a positive rho, but and positive and negative pressure here. This is the zeros. So that's the difference between it's a mirror image of the phantom energy. And in our case, we just live on the diagonal, actually. Even in the phantom matter case, if you didn't have the condensate, you would live, you still have a de Sitter phase, the Sitter type equation of state. Total rho equals minus P. That's because the Chern-Simons anomaly terms contribute negative terms in the stress energy tensor, as I said. Is that okay, Joan? You want me to say more, or?
No, I mean, of course, I know what is phantom matter.
Yeah. No, but I mean,
I just wanted to help people because this is not very common.
Indeed.
I introduced this name in 2006. At that time, I was talking about a model which was called the Lxcdm model. And it was interesting because phantom matter, it satisfies the strong energy condition like matter. That's why I suggested to call it matter, despite it is phantom, because the energy density is negative. But this region in the parameter space of the equation of a state, it still satisfies the strong energy condition. And in this sense, it has a reason for this name.
Right.
But, yeah. But in our case, it played, well, a different role. Well, it is the same equation of a state, but of course, the framework is very different. It is also interesting to notice that the phantom matter also appears in wormholes. You remember this footnote that we added to our review?
Indeed. I didn't have the time to discuss this.
Yes, because it appears, because in the mouth of the wormhole, you need to have energy density matter with negative energy density in order to stabilize the whole topological structure. This is something that I didn't know in 2006. I learned it later. So this is, yeah, a very kind of exotic substance, but it appears in different places in cosmology.
Yeah, in this context arises naturally, as I discussed.
That's right.
Okay,
naturally, I don't know whether it's naturally, it arises microscopically, let me put it.
Yeah.
Okay, I see that Matteo Luca has another question, but unfortunately we don't have time. So Matteo, If it's okay with you, you could ask it perhaps at the end of
Yeah,
today's,
can I also do 1 second? I just want to, because of several of us belongs to this network, all these matters, we are in a cost action. We have a training school in Corfu this year, whether it comes natural or not. And all these matters, there is a training school in quantum gravity, you see, which the links are here, and then it's followed by a second annual conference. So I wanted to close my presentation by advertising people who have invested, or your students. You could encourage them to attend. Several of us, Joan, myself, Jose Manuel Carmona, I think is among us today, who is the leader of this action. So that's all I wanted to say. Thanks very much.
Thanks, Nick. So now the next speaker will be Armand Chafiello. So please, Armand, if you want to share the screen, he will talk about parameter discordance in current cosmology, projection in the primordial power spectrum. Thanks, Armand.
Okay, so let me share. Okay, so first of all, I would like to thank Juan and Adria for inviting me to this session. I wish we were in Rome. It could be fun. I mean, particularly after the last night match. But anyway, hopefully after 2 years, we can be in somewhere interesting. Okay, so I'm going to give a presentation mainly about how we can project the current tensions on the primordial power spectrum. This is an attempt that I think some group have approached, but it's a pretty complicated approach. And but we want to see that if it is possible or not, and if it is possible, what will be the theoretical implications. Some review that I think these days, in last couple of years, it has become very known to the community that, yeah, we have a standard model. It works very well, 6 parameters. And, you know, it satisfies different observations pretty well. When we look at the residuals with the Planck data, this is amazing, you know, how this model performs. And not only in the temperature, but also in polarization data. We have the supernova compilations. Again, you know, it looks amazing that how this model can, you know, feed the data, as well as the Barron acoustic oscillation results from the final EBOS collaboration. So everything looks good, and this model looks like a nice combination of assumptions, because I call it a combination of assumptions because the standard model is basically a combination of assumptions. We assume FLRW metric, we assume homogeneity, isotropy of the universe, we assume flatness, we assume lambda dark energy, we assume power law primordial power spectrum, and they are reasonable. They are all reasonable, but the fact is that still they are assumptions, and it's always important to question these assumptions, that whether we should go beyond them or we should not. And we hope that, you know, some of these cosmological tensions might be in fact a hint to go beyond the standard model, because, you know, it's already have lived for long enough to be broken. Okay, so it's a combination of reasonable assumption, but, you know, as you know, we have seen, particularly from 2013, when the first release of the Planck data come out, we realized that the Planck data is, you know, preferring a Hubble parameter of about 67, assuming a Lxcdm universe. At that time, the Shoes analysis was about 73 with pretty large error bars. So it was not that serious, but as time passed, things become worse in a sense that Planck basically could control their systematics on 217 gigahertz channel, but the results on H0 converged more on 67 with the smaller error bars. And the Adam Rees groups and Shoes collaboration basically also, you know, add more information to their calibration and analysis. And then they got to values which were even higher than their previous values, and with smaller error bars. So the tension rise to more than 4 sigma, and which looks like a serious problem now. I mean, because, you know, the standard model with all its pillars and aspects seems not being really able to provide the value which we observe locally. So one can put blame on different things, but certainly this is something that so far there is no consensus. One thing which can go beyond that is not only about H0, we have also sigma 8 tension, as we know that by the shear weak lensing analysis from the kids from the CFHD. Also there's, you know, we can see that, you know, the constraints which we get for the sigma 8 or S8 is not really matched with what we derive from the best fit or parameter or model parameters from the Planck. And this has been remained persistent too, and which has been making it pretty difficult to understand what to do. So we have S8 tension, we have Hubble tension. I would like to mention about this omega baryon matter H square that we noticed about between the Lyman alpha forest and CMB, as we shown in some of our papers, that it's nothing to do with H0, but just the Lyman alpha from the BOSS collaboration had some issues. The Hubble parameter was much lower than what we could expect. So if we allow curvature, things become slightly even worse, because then Planck data alone might even prefer a non-flat universe. So yeah, we are dealing with a situation which is pretty complicated, and we are seeing multiple kind of inconsistencies here and there. So how to go beyond the standard model, or basically from a vanilla ice cream to some fruit ice cream? So it's interesting, there are ways to do that. One good way is that basically to finding features or deviations in the data beyond the flexibility of the model. This is something which is certainly a very important aspect. Basically ruling out a model, that seems to be always the very best first approach. Or we can come up with litmus tests, which we can falsify a model, yes, no, or finding tensions among different independent data, which basically either hints to some systematics, or it might basically hint that the model is not compatible, or it's not powerful enough, have enough flexibility to explain all the observation. From theoretical phenomenological aspect, we can come with new models which can explain the data better. And this should be systematic, it should be statistically significant, which is a very difficult thing, because Lxcdm is already a very minimal model. It has only 6 parameters. So it's very hard to beat this model using something like a Bayesian evidence. As just some historical examples, which are already back to history, for example, about some of these litmus tests, with Alexei Starobinsky and Varun Sani, we introduced this OM family of the diagnostics. For example, OM-H square was designed to compare the observables of the CMB and baryon acoustic oscillation, and we noticed that there is a significant issue between these observables. And at that time, we basically speculated that it should be most probably due to the systematics, because the quasar BAO data was just the first time we were detecting BAO from them. But results didn't change much in 2021, 2020. Still, we can see that this tension persists. So we can use litmus tests. We can evaluate the tensions. These are some of the works with Gongbo a couple of years ago after DR14 analysis, that we tried to see how, assuming a model and using different data, we can evaluate the level of tensions. And as we can see, the 2 data which clearly show a serious level of tension is Lyman alpha and Hubble constant. So the problem is more than H0. Things has not been really changed much. As I said, the new release of data didn't change things much, as well as the Reese analysis, extended Reese analysis, just make the situation worse. So we are observing multiple suspects. This combination of different problems that are very difficult to address. And it's very difficult to address them with some minimal modification to the standard model. So how we can resolve? So some people might say it's statistical fluctuations, which is not anymore, because some tensions are really at high significance. The probability would be very low to get there. Systematics in one or some of the data. This is what I personally bet for, because for a very interesting reason, that we had this paper a couple of years ago, which we tried to argue that it's very difficult to make things fine with minimal modification to the standard model. So we need really many different extra degrees of freedom to solve all these tensions. And so this more look like that, we have some problem with the data or some of the data. So I would not be surprised if you find systematics in one or some of the data, not only one of the data. Most of the community have been working on the extended models on new physics, which is interesting, which is fun to do from theory versus from phenomenology. However, extended models usually have more degrees of freedom and results to this inflated larger contours, which they have a better overlap, and then they call it, okay, we are reducing the tensions. It's okay to do that, but these are usually overselling. And we are not really solving the problem. We are just inflating the contours. I think the mean values also, we need models which, if we really want to solve the tensions properly, and if the data is really correct, we need the mean values, let's say, of the Hubble constant to drastically shift to the higher values rather than just increasing the size of the contours. Okay, so if I want just to summarize, what can we do? We have the standard model. It has many different aspects, and how we can, attack that. We can play with the flatness, isotropy, homogeneity, certainly important issues. We know that we have had things from the WMAP and Planck about the spherical asymmetry, and these issues are still there. Dark energy is lambda. Many attempts to deal with the dark energy at low and high redshift. We have premodal power spectrum, dark matter, and the metric FLRW. So, yesterday I gave a talk about the dark energy part, about our phenomenological dark energy model, as well as early dark energy, which I'm not going through that. But yeah, one thing is very clear, that none of these models are really able to resolve the tensions properly. So early dark energy models, late dark energy models, considering the covariance in the data, none of these models are really capable to resolve all the tensions. Maybe another hint that, maybe some of the data has some systematics. But today I want to go to a completely different aspect of the problem and trying to see if we can project the problem on the form of the premodal power spectrum. So why premodal power spectrum is important is that most of the single field inflationary models resolves to the power law form of the premodal spectrum, which is a part of the standard model. But we can have many other inflationary models. We can have many, even in single field inflation, we can have different potentials which resolves to non-powered or features in the form of the premodal spectrum. So there have been numerous attempts just before WMAP 1 data comes out in 2003 or 4. That now we have the data which basically angular power spectrum of the CMB can cover up to range of the thousands or so. So why not trying to reconstruct the form of the premodal spectrum in a model independent way? So there were many attempts with Sarah Bridle in those days, George Statue, I was doing my early PhD times. So many attempts were going on. And still this is a subject which is very important for the CMB people to look at the reconstructed form of the premodal power spectrum. These are some of the results from the official Planck papers that when we try to look at the form of the premodal power spectrum and see if the data suggests any feature. So what we can see is that the data is consistent with the power law, but we have flexibility. But why is it important? It's important because power law is fine, but there are some other models which might be also consistent to the data. And if this is the case, the consequences on the background parameters would be also important. So what does it mean? Means that I may have some very strange forms of the premodal spectrum, which basically, let's say here we discussed about the Wick inflation with Derived and George Smoot and Alexis Starobinski. We have a series of papers that these models basically are single field, pretty interesting models. They're internally consistent models with a reasonable amount of non-Gaussianity, but they produce features in the form of premodal spectrum. And these forms not only satisfy the CMB, they also can satisfy other observations, but they might result to different background parameters. So this is a very key important point that when we assume the power law, we have basically ANS, NS, but the background parameters combination basically is going to satisfy my CMB observations. But if I assume another form, then maybe I need the different background parameters to satisfy my observations. So this has been one of the most important things in these direct reconstructions, which we have been, again, I have been involved from many years ago from my late master course, which I've been working consistently at this on direct reconstructions of the premodal spectrum. Here we developed a method called modified Richardson-Lucey deconvolution, which have many different stages. But this is a very important approach to allow you that when you have different parameters for your background, it basically reconstructs the form of premodal spectrum, which can satisfy the observable which you are basically testing for. So for example, here is one of our old papers dealing with the final WMAP data, which we showed that the red contours are for the power law. These are the valid points in the background parameters. And then we showed that, well, no, if you allow some features in the premodal power spectrum, larger area would be allowed. And it basically led you to have different values for the background parameters. How I can relate it to the Hubble tension? Okay, it's simple. So we says that instead of fixing my background parameters, omega matter of 0.31 and let's say Hubble parameter of 67, I keep omega matter H square the same as omega matter H square as what we derive for the standard model. And why omega matter H square? Because omega matter H square is a very physical quantity associated with the position and the height of the acoustic peaks in the CMB. So I don't want to touch that, but I'm gonna use a different value of matter density, which here we used matter density of 0.259 or 0.26 and Hubble parameter of 74. And then I said, okay, I fix my background parameters and now I reconstruct the form of premodel spectrum. So what you see in the top left panel, the blue curve, is in fact a reconstructed form of the power spectrum, which is more happy with the Hubble parameter of 74 and omega matter of 0.26. And if I use this model instead of the power law fitting to the data, this is what we get in the bottom plots. As we see in the sigma 8 omega matter contour, now my reconstruction contour not only satisfy larger value of Hubble parameter as we see in the right contour, it's just at the middle. It also satisfies the kids and the weak lensing things because it brings the matter density lower and basically satisfy the S8 or sigma 8 omega matter inconsistency. So we basically we are going to hit two targets at the same time with the cost that we have very weird features in the form of the premodel spectrum. Okay, I know that there have been similar attempts by other groups to come up with such a form, and mainly they failed. I would like to advertise the power of the MRL here because it has the ability to generate various features with different amplitudes and frequencies at different wave numbers. So this is something which give this very strong capability to the MRL to basically come up with the different features at different wave numbers. So we extended the work. There was a work by the Ryan, my postdoc, who is going to leave soon next week back to US for his next postdoc, that we tried to say, okay, let's have this form. We have the power law. Let's come with some deformation model and see that, how data basically suggests. And it is interesting that in fact, one can come up with very nice values for the Hubble parameter if we come with these deformation models with the Hubble parameter of close to 72. Which is totally consistent with the recent analysis, and it is also consistent with the CMB data very well. Again, for the cost that we need such features in the form of the premodel spectrum.
3 minutes, Sharman.
Okay, 2 minutes or 5?
3 minutes.
3, okay, good enough. So, okay, so some issues is that is it natural to generate such a complex form of the premodel power spectrum from inflationary scenarios? This is what we are currently working on, and we got very interesting results. So we are basically generating a form of inflationary potential, which can generate such a feature in the form of the premodel power spectrum. So it can basically say, okay, so it is not very much unnatural. We need, of course, to use polarization data. We need to explore underlying parameter space as well, that all these might be connected to the A lens issue. And one reason is that the similarity between these two plots, which I show here, this is from one of my old papers with Derived and Suradip in 2014, which when we switched off CMB lensing and we tried to fit the data with just features in the premodel spectrum. And this is what we get, the red fluctuations. And this is what we get now. So all these things might be connected. This is what we are exploring now, that if this A lens not equal to 1, CMB lensing and all these issues are connected. So it's a very open question for us. And hopefully soon we would have some results on that. So the current status, open problems are open, many tensions and hints for various systematics. That's what I would say that is very important. There are many models proposed, but I would say that none of them is really convincing. We should wait and see how data would evolve. It's not possible to resolve all problems with minimal modification standard model. Again, this might hint to possible tensions. And one thing very important to test for systematics is that the model independent consistency test between various data. So this is what we did, for example, for the SDSS collaboration with Ryan, that we tried to test consistency of BAO data and supernova data to say that independent of any model assumption, if they're consistent or not. So the future would be basically very much dealing with the assumptions, systematics. So we should realize, I would like to emphasize that the high quality of the data, the role of systematics would be more important. So many of the tensions we see now might be because of the systematics in the data plus precision. When the precision goes higher, the systematics would basically makes more tensions. So we should be very careful about this. And the future perspective, basically, we would have the same problems.
1 minute.
Yeah, we would have the same problems, but we need just to realize that, we can get help from the other observations and like a, large scale structure to basically find the formulas of the pre-model spectrum. So my last page, the standard model works fine, individually fits the data, but it fails to fit to combination of the various data. It opens way for the competitive algorithms, alternatives. Early universe scenarios might be able to help. And systematics, again, we might need new physics and systematics, but we should really, really try to understand what is going on with the data. And maybe the first attempt would be to test lambda, dark energy, and popular pre-model spectrum, and with the new data, basically, to make sure that we are using the proper data. Yeah, thank you.
Okay, thanks a lot. Perfectly on time. So Professor Nick Mafromatos has a question. Please, Nick.
Yes, very nice approach. I would like to ask whether in this approach you should also take into account dust models, because dust models for the universe might contribute to the tensions. There are claims that it depends what dust model you're using. So are you going to combine with this analysis more mundane explanations in the tensions?
Thank you so much, Nick. Certainly an interesting idea. I mean, at the moment, we are trying to have a most simple approach to make things clear how it works. But certainly, when we are clear about the basic data, for example, the next attempt is just to test it with the polarization data. I'm not sure that this works with the polarization data. But if it works with the polarization data and it works with the temperature data, then certainly, yes, then I will try to look at the other things. And the dust model is certainly something interesting to look at, yeah.
Very good. Thank you.
Okay, I see that Matteo Luca has another question for Arman.
Well, yeah, it was a very similar question to Nicolaus' one. I mean, you showed at some point a plot where you showed that with Planck you could explain both tensions and reconstruct a power spectrum. But I have the feeling that if you include like BAO or any other anchor that could kind of extend your lever arm, it would be much more constraining than just using Planck, right? Have you considered that in any of your analysis?
Well, again, these are all the next steps that we are trying to do. The first one, as you said, yeah, polarization data. After that, we should look at the BO data. I mean, since the background parameters are same or consistent, I would not expect much problem with the BAO. But with the BAO and supernova combined, yes,
yeah, exactly.
Might be some issues. So we will see. I mean, as I said, I personally believe that some of the data has some problem. So I'm not really hopeful that there should be any solution to these current tensions. But yeah, we will see. Okay, yeah.
And maybe also last question. Do you expect the impact of, say, for instance, CMB spectral distortions to play a major role together with the other future generation probes that you mentioned, like because it would probe the K range up to 10 to the 4. So I was just wondering whether you would insert spectral distortions too in this set of data of missions, although they are not really planned.
Well, again, let's see. I mean, so far, again, there's no CMB4 mission, right? We were very hoping for the core, and the core failed, right? We have Lightbird, but yeah, I mean, and again, even at the small case, we have the problem that we cannot really make things much better, right? But at the high case, certainly we might do better, but again, it depends on what we would observe.
Okay, yeah, I don't know if is there time for another question, or are there?
Unfortunately, not. So
then thank you very much.
At the end of the session talk, yeah.
Yeah, thank you very much then. Sorry.
Okay, thanks a lot, Arman. So let's move to the next speaker, Joe Toda. He will talk about extra component solutions to the Hubble tension with Big Bang nucleosynthesis.
Can you see the slides? Turning page.
Yes.
Thank you for the opportunity to speak today. Today's presentation is based on these papers, collaborating with Osam Seto. If you take an interest in my presentation, please also read these papers. The Lxcdm model has been successful in explaining the evolutions of our universe. However, the tensions of the Hubble constant is appeared between the distant observations, which is based on Lxcdm model, and the local observations, which is the direct measurements. To solve these stations, several ideas have been proposed. Among such ideas, today, I would like to focus on the extra radiations and early dark energy to solve the Hubble station. And I would also consider the extra component solution to the Hubble station and the consistency with Big Bang nucleosynthesis. And I would like to summarize that extra radiations and early dark energies are the promising solutions, but two scenarios are limited from Big Bang nucleosynthesis measurements. First, I would like to explain what is Hubble stations briefly. The Planck team, the measurement of the cosmic microwave background anisotropy reported the Hubble constant is around 67, and other distant observations like baryon acoustic oscillations or Big Bang nucleosynthesis also reported around 67. On the other hand, the local observations such as Cepheids, supernovae, or TRGBs reported a higher Hubble constant around 74. I recognize that this distinction indicates beyond Lxcdm physics. Next, I would like to explain how the distant observation of the Hubble constant is derived, because I would like to explain how the extra components to solve the Hubble stations. Especially, I focus on the cosmic microwave background anisotropies, and we measure the cosmic microwave background anisotropies, and this information have the informations of the angular size zeta star equal R star over dm star, where R star is the comoving sound horizon at the recombinations, and dm star is the comoving angular diameter distance. And zeta star is directly and strictly measured 1.041 times 10 minus squares by Planck genes. If you substitute these equations, the relations of the cosmic times and redshift into these definitions equations, you can derive that the Hubble, the angular size zeta star is proportional to the Hubble constant over scalar root rho in the early universe. So when we introduce extra components or increase rho in the early universe, we can derive a higher Hubble constant. The promising way to increase rho in the early universe to introduce extra radiations or early dark energies. Of course, there are another solutions, but today I would like to focus on these two solutions. So immediately, I would like to talk about the extra radiations. The radiations consist of photons and neutrinos in Lxcdm model, and the parameters, the relativistic degrees of freedom, is consist of the neutrino 3 plus 0.046 E plus E minus annihilations. And when we introduce extra components, extra radiations, we increased an effective like this. The left figure shows the results of Markov Monte Carlo analysis, and you can see that the relativistic degrees of freedom relieves the Hubble stations. The x-axis is the relativistic degrees of freedom, and y-axis is the Hubble constants. And we include the data, the CMB from Planck, and light curves from Parthenons, and baryon acoustic oscillations, and supernovae from this. The right figure is from the Planck papers, and you can see and this figure is without local data and includes only CMBs. So you can see the impact of the local data from this. So the relativistic degrees is the promising solutions, but you may worry about the consistency with Big Bang nucleosynthesis. Introducing relativistic degrees of freedom, higher and effective, is, in other words, the additional component increases the expansion rate of the universe, the decoupling temperature of the weak interactions, and neutron to proton ratios. Therefore, higher and effective leads to higher helium mass fraction YP like this. The orange regions is the measured values by Avers, and so the higher relativistic degrees is disfavored from the measurement through the YP measurement. And higher relativistic degrees also lead to higher deuteriums, and from the observations, the green region is the measured values by Kukes, and so higher relativistic degree is a little favored from the deuterium measurement. This tendency is also shown in the Kukes papers. As a result, the blue contour, which includes the Big Bang nucleosynthesis status, we include the helium mass fraction measurement and the deuterium measurement as the Big Bang nucleosynthesis status, and blue contour with Big Bang nucleosynthesis is limited, is disfavored higher relativistic degrees and higher Hubble constant by helium mass fraction measurement. Next, I would like to treat the extra early dark energies. And in the early dark energy scenarios, energy densities of dark energy in the early universe was much larger than today's. And after the critical point, the energy densities decreases faster than background energy densities do. In our analysis, we vary the amount of early dark energies, omega E, as the parameter omega EDE over omega lambdas. And referring to the previous research, in this analysis, we fix the critical points at redshift nearly equal 3000, and this is the around matter radiation equality and before the CMB photon last scattered, which is redshift equal z equal 1000. And after the critical point, we decide to early dark energy decreases like kinations. This figure shows the results of our analysis with early dark energy scenarios. The x-axis is the amount of early dark energies, and omega EDE over omega lambdas indicates the densities of early dark energy states of cosmological constants. You can also realize that early dark energy relieves the Hubble radiations, similarly to the extra radiations. And in addition, early dark energy doesn't increase the expansion rates of the Big Bang nucleosynthesis epoch. So early dark energies doesn't change the helium mass fraction measurements. And so early dark energy scenario is matched the measurements of the helium mass fraction measurements. However, in the early dark energy scenarios, the baryon acoustic densities increase to adjust the CMB fit, and baryon acoustic densities increment lead to decrease the deuterium abundance. So when we introduce early dark energies, the fractions of the deuterium decreases. So the deuterium measurements in the green regions is this lines, and so you can realize that the higher or larger early dark energy is disfavored from the deuterium measurements. Therefore, the blue contour, which is the analysis with Big Bang nucleosynthesis measurement, helium mass fraction measurement, and deuterium measurements, shows the less amount of early dark energies and the lower Hubble constants. And the red contour is the without the Big Bang nucleosynthesis. This and so to sum up the early dark energy scenarios, a higher early dark energy is disfavored from deuterium measurements. This result is different from the extra radiation case, which is limited by the helium mass fractions measurements. Finally, I would like to summarize today's presentations. Both extra radiations and early dark energy are the promising solutions of the Hubble issues. But the extra radiation is limited by the helium abundance measurement, and early dark energy is limited by the deuterium abundance measurement. I would like to close my presentations. Thank you so much for your kind attention.
Okay, thank you very much, Joe, for this nice talk. And now it's time for questions. Please raise your hand, your virtual hands, please. Okay, Sebastian.
Thanks, Joe. I would like to ask you, do you have something to say about lithium?
Sorry, sorry, once more, please.
Yeah, you have studied helium, deuterium, and the question is, do you have something to say about lithium, the abundance of lithium at Vivian?
We don't include the data of lithium, and maybe so I can't answer for the lithiums. Sorry.
Okay, don't worry. Yes.
Okay, more questions. I have one actually. You have mentioned that you fix the redshift at which the transition happens in early dark energy, where you find the peak in the fraction of omega dark energy. Yes. So you fix the critical point, right? Okay. So have you studied what happens if you allow it to vary in the fitting analysis?
So I haven't studied.
Okay.
And okay, yeah.
Okay. Okay, thanks. Professor Mavromatos, please.
Yeah, a very quick question, which is related to the previous one by Sebastian on lithium. Is your model of early dark energy consistent with BBN, with Big Bang nucleosynthesis? Does it affect the abundance of the elements, or did you check? Or
we check only the helium mass fraction and deuterium measurements.
Yeah, but I mean, do you think it could affect the BBN, or?
So are you asking the consistency with other like the helium-3 or
yeah.
lithium?
Okay, this is my question. Yes, and that was, I think, probably Sebastian's as well, I guess.
Maybe increasing omega pH scale is the tendencies of introducing early dark energy, and so also helium-3 decrease. So I think that helium-3 is also disfavored from the measurement.
Thank you.
Okay, thanks a lot, Jo. So there isn't more time for questions, so let's proceed. It's time for Eoin Colgain's talk. Hi, Eoin. Can you share your screen, please?
Yeah, just a sec. Open my mask.
Okay, so Eoin will talk about a compelling resolution to the H-naught tension. Thanks.
Okay, so as long as you can see my screen, that's great. Okay, so first of all, thanks for the invitation. Thanks for providing the platform to give this talk. So yeah, I'm going to give a talk about H0 tension, and I bounce about a lot on where I think this thing is going. At the moment, I think it's going in a particular direction, and I have some, let's just say, hints that it may be going in that direction. And just before I begin, let me make some comment. That if you take dark energy seriously and you look at H0 tension, what H0 tension, because all the local H0s are biased high relative to Planck lambda CDM, it essentially pushes us into the phantom regime. So if you think this is like a resolution within dark energy, that's sort of at odds with a quantum field theory description or any sort of effective field theory description of dark energy. So even just at face value, if you look at the values and you see that all the local determinations are biased high, this probably tells you that there's something radical that has to happen in the dark energy sector for us to get some physics out of this. It's just worth thinking about. Okay, so let me move on. So this is essentially the problem, and Armin gave a very nice overview of the situation earlier, and he has stressed the assumptions. So cosmology essentially proceeds by assumptions, and there's a whole load of them. So Armin had like a slide with at least 6 or 7 assumptions. Now, if you proceed by assumptions, contradictions are inevitable, right? So, and whenever you bump into these contradictions, you have to ask, are they systematics, or is there something fundamental going on here? So this is basically more or less the status where we are at the moment. And this is taken from Eleanor's very nice review. And again, this is the biasing that I find very interesting, that all local values are essentially higher relative to, let's say, any sort of inference that depends on a model, lambda CDM. And so what this tells you is if you try to replace lambda with quintessence, you can actually prove that you would be moving in this direction here. So quintessence dark energy, which is the simplest effective field theory of dark energy, is essentially ruled out. So it's a very strong result, right? Just even TRGB will do this for you. So yeah, certainly it's very interesting. Let me move on. Okay, so yeah, another comment. H0 tension only makes sense within the context of FLRW, or the cosmological principle. So if there are discrepancies in FLRW expectations, then logically they take precedence, and H0 tension is ill-defined. So you can't really discuss H0 tension unless you're assuming FLRW or you're very confident of FLRW. So it is prudent to make sure that we are not discussing a problem that is ill-defined. Now, let me just tell you that, well, this is something I've learned, I guess, over the last few months, is the local universe is extremely messy. Determining H0 is not easy, and astronomers are doing fabulous work. And just let me point out, because the next speaker is going to give us a talk on gravitational waves, is that this gravitational wave event is at 40 megaparsecs. Now, we're somewhere in here, and the Shapley supercluster is roughly at 200 megaparsecs. So you're somewhere in this local universe. that is being mapped out by Brent Tully and his collaborators. And so I took this from their 2017 paper. It's a very nice cartoon. And your problem is essentially, even if you have the distance, you will get a redshift, but which part of that is the Hubble flow and which part of that is some sort of peculiar motion. This is an extremely difficult problem. And just to highlight this, in the aftermath of the HST key project, where they gave the first modern determination of H0, McClure and Dyer, basically they went through the data and they sort of said, well, what does H0 look like on the sky? And they gave different values of H0. And so again, in some sense, whatever we're calling H0 is some sort of average over all of these values. So again, if you just have one result and it gives you a H0, what can you really infer? You really have to you have to take all of this into account. So going forward, gravitational waves will give us a determination, but we need to deal with these peculiar velocities. I guess then the problem is the same. Okay, so let me ask a question. Is there a maximum H0 that you can get in FLRW? And so we presented some analysis earlier in the year, it appeared in May, that basically works on certain assumptions. So gravity is described by general relativity. So I don't see any experimental evidence for modified gravity, so I'm not going to go in that direction. If LIGO turns up something, then I'm happy to take a look at it. Age of the universe from globular clusters. So there was a recent determination by Bernal et al. It's essentially consistent with Planck. So 13.5 plus or minus 0.27 gigayears. We assumed that Planck had accurately determined this combination here, and we subtracted the low multiples, which is basically a strategy that has been employed by various groups, I guess starting with Ruth Durer and her collaborators from 2010. So this basically it inflates your errors a bit, but it allows you to sort of treat the late universe in a more model independent fashion. So this just gave us some extra freedom here. We took a prior on MB, which George has reminded us and various other people have reminded us that we shouldn't put a prior on H0, we should put a prior on MB, because this is what is coming out of the Shoes analysis. We assume matter, we exist, and we assume the variable dark energy sector. So we assume that basically the Hubble parameter in some sense is an analytic function in Z. And then we combined with various, usual data sets, BAO. We took the BAO all the way out to Lyman alpha. Again, there may be some discrepancy at high Z, but 2.3 or so, some mild discrepancy. But we decided to use it all because, DESI will eventually come and give us a whole load of BAO. And it's good to see, basically the prior on this MB in supernovae fighting with, whatever your prior is in RD or whatever early universe physics it is that fixes RD for you. So these guys are essentially in competition. And we took cosmic chronometers. So basically the result we got was this: H0 is 71 plus or minus 1 kilometer per second per megaparsec. Now, just to point out that this is more or less representative of what you would expect in an early dark energy model. So there's a recent paper by Mark Trodden and various collaborators. And so again, I mean, from our end, I don't think it's very surprising. Like our setup was more model agnostic. So they get this value 71.19 plus or minus 0.99. Their BAO is, they don't go as deep in redshift with the BAO, but they have a very concrete model, and they're basically the radius of the sound horizon is essentially fixed by the model, whereas for us it's essentially a free parameter. So we had to basically let this guy. Our RD was taken as a free parameter. That's what you need to do to basically get a high value like H0. If you don't take it as a free parameter, you will be down below 70. So the values of, if we do converge to 73, we can go back. Eleonora gave us this optimistic average here, or this ultra conservative one, it's about 73. So if we do converge there in the end, there's no problem, you're at 2 sigma. So clearly FLRW, we can resolve this problem, the H0 retention problem, but we need an early universe resolution. So we can't have a late universe resolution. But then when you read any of these papers, basically people are very, okay, they tell you, okay, I can resolve H0 tension, but then there's a problem with other tensions. So for example, cosmic shear. And you can see that this is, again, taken from this Mark Trodden et al. Paper, and it's pretty explicit. Yeah, okay, we clearly have a problem. So the question, I guess, for Mark Kamiankowski is later today is basically, when should we give up on ED and its variance? Basically, or is there some extra mileage to be seen in this direction? And I think from our analysis, we would say that this is the only thing left on the table within our assumptions, an FLRW, which is a strong statement. Okay. but still, let's move on. Let me tell you that there are some results. There is some experimental evidence or hints that basically things are not very rosy in the FLRW paradigm. So there's a very nice review by Dominic Schwartz and his collaborators, and they basically review a whole lot of earlier results on radio galaxies. And the basic idea here is that, you know, basically, if you look at the CMB, we subtract the dipole. So there's a much larger anisotropy in the dipole than the other multipoles. There, one is at 10 to the minus 3 and the other is at 10 to the minus 5. So we have to subtract that. And from that, we basically infer our velocity with respect to the CMB. So now you can, and that's all in heliocentric frame or local group frame or whatever frame you're in, some local frame. Now, what these groups have been trying to do is basically test that. Can I recover that velocity or that particular dipole by basically using radio galaxies? And so what they do is they roughly, and this nice table is taken for Dominic's, and there's a whole lot of earlier surveys of radio galaxies. And the punchline is basically that they more or less agree on the CMB dipole direction, but they disagree on the magnitude. And the discrepancy here is somewhere about 2 or 3 sigma. So it's not very alarming, and this thing has gone under the radar, but various groups are aware of this. And it seems like this is, you know, the results are consistent. So yeah, in 2020, Subir Sarkar and his collaborators, you know, they basically took this and they moved to quasars. And again, the conclusion is more or less the same. So dipoles agree in CMB direction, but not magnitude. And what they're claiming here, based on some simulations, is just basically just reshuffling their quasars and doing it a large number of times, is that they're claiming that the discrepancy, you know, the dipole that they infer from the quasars disagrees with the CMB dipole at, I guess, 5 sigma or almost 5 sigma. Now, one thing to stress, I mean, this is essentially the redshift distribution of their quasars. They're reasonably deep. So yeah, I mean, you could worry about contamination, particularly with radio galaxies. Like basically some of these results are, you know, these could be local radio galaxies that are basically contaminating your analysis. But here I think it's a little clearer, but still this is probably an issue, and it's something somebody should look at. And to point out that probably the methodology in this and the methodology in this is the same. So it may be serious, but if you don't like the results, you can always question the methodology. The systematic should be different, right? This is essentially coming from a satellite experiment. And as I like to joke, radio telescopes don't fly yet. So let's move on. Anyway, so dipoles aren't very intuitive, I think, unless, you know, you want to spend 6 months learning about them. Yeah, we were interested in this, you know, okay, so Holly Cow, if you look at strongly lensed quasars, or maybe the TT Cosmo collaboration, they have basically this trend where H0 decreases with the redshift of the lens. And we were very interested in this for a while. You know, what could give rise to this? And there seems to be some analysis in this paper by Millen et al., and they sort of say it's, you know, it's not an obvious systematic, but it seems to be there. And so when we were writing up this paper, we sort of decided to plot this against the CMB dipole to see what we would get. Now, you've got to bear in mind that these are just the central values, and there's like large errors, so you can see the errors here. But what you do find is the 2 largest values of H0 are aligned with the CMB dipole direction. So this is sort of, yeah, it's very intriguing. And just to spell it out, what these people are saying, and what Subir's been saying in particular, is that there's an extended anisotropy that goes very deep in redshift, and he's even claiming it comes all the way down to z = 0. So, you know, this seems to be consistent with that. You know, you could imagine some sort of effect in time delay, and you know, that basically would result in these slightly higher values. So it's certainly intriguing, but it's a very small sample. And so basically motivated by that, I decided to have a look at some Pantheon data, because with Pantheon, you know, Pantheon starts off at z = like 0.01, and you can go all the way up to z = 2.3, but it gets very sparse. You can certainly go to z = 1, it's fine. And so my first, this is essentially a letter we've got on the archive. In my first go of this, I basically took some ad hoc pink region. It was completely ad hoc. And decided to split the supernovae sample and basically fit the Lxcdm model with basically some lower bound on redshift. So what you find is basically up to some redshift, say roughly 0.5, that, you know, basically it's consistent, but then beyond that, this pink region has a slightly higher value of H0 than its complement, which is the other region there. Now, I should say that we were sort of motivated by some earlier paper by Cook and Lyndon Bell, where they had found something similar. This is more or less 2 sigma, but they had some sort of 1.2 sigma or so observation for something similar, some deviation beyond, let's say 0.53, I think is what they have in their paper. We performed some simulation over a large number of mock realizations of, lambda CDM type data. And yeah, you can confirm that this is more or less beyond 2 sigma. Since then, I was reminded that, this isn't very scientific, that I should basically scan over the sky. And so here's a scan over the sky, and it more or less recovers the same thing. So basically, this dipole is, I don't know, it's difficult to infer from here, but it will be somewhere to the north of this line here, somewhere in this direction here, which I guess is RA, well, DEC probably about 30. So it's in here somewhere, hard to know what it is, but it's in there anyway. And what you're seeing is somewhere, let's say comparable over 1.5 or 2 sigma. And there's some patches in here where it's a little bit more, pronounced. And this is essentially where Suber et al., where Seacrest et al. Say their dipole is. This is where Cook and Lyndon Bell say it is. And this is the CMB dipole. Now, the one thing that I've realized since is that, if you look at the Pantheon data set, you can just pull it apart. And here's basically, this is just supernovae below 0.2. It's essentially 411 supernovae, and you can do exactly the same exercise. And again, it's again low significance, but there are slightly higher H0 values in the direction of the CMB dipole. One thing to point out, if you look at the Pantheon data set, there's not very good coverage in the DEC direction, but there is reasonable coverage in RA. So this may explain why we get these essentially lines. And this is basically the same thing if you look at matter density. So we know that if H0 is high, this should be low. And it's more or less telling you the same thing. Again, it's less than 2 sigma, so not much to look at. But it's certainly consistent with a large, well, I should say large anisotropy. I mean, an anisotropy that's extended in redshift. It may not be very pronounced, but it doesn't make a difference which frame you're in. This should all be in CMB frame. There's a nice paper by Ashok Singhal recently where he tries to recover the dipole in a model independent way. So he's not fitting lambda CDM, but yeah, from the Pantheon data set. Okay, and so basically you can extend this to whatever other data sets you have at your disposal in the late universe. And there's one due to Risoliti and Lusso, which is essentially some quasars. And the assumption is basically that there's some relation between luminosity in X-ray and luminosity in UV, and there's these two parameters beta and gamma. And so you can exchange them or for essentially fluxes, and then fluxes are essentially what we observe. So, but once you plug in the luminosity distance here, then we have access to, pardon?
3 minutes.
3.
3 minutes.
Good. Yeah. So we have access to basically cosmology. So we can say things about cosmology. Now, there is some discussion about whether beta evolves or whether or not these are even standard candles at all. Gamma is probably some reasonable thing. It doesn't, it always seems to be about 0.6. There's a lot of intrinsic scatter, I should say, in these data sets. Beta could be evolving, but if you look at let's say the 2015 paper, Risoliti and Lusso are adamant that basically between 0.5 and let's say 1.5, that there's very little evolution in beta. We took a slightly higher value, 0.7 and 1.7. That's because in this recent paper, they sort of say you should do cosmology from 0.7, get rid of the low redshift quasars. But essentially this is 1,000 quasars. And again, I'm not plotting H0 or sigma H0 here. I'm actually plotting, I'm plotting basically some variation in beta. And beta is basically degenerate with H0. And because this sign, gamma is 0.6, this here is actually negative. And so, of course, this DL goes as 1 over H0, right? So you've got 2 negative signs give you a positive sign. So an increase in beta is an increase in H0. And so again, one would have to look at the coverage, but again, we're seeing the same thing here in, and this, I've MCMC'd this, and it's essentially over 2 sigma, just at this point here maybe a bit less. So again, relatively low statistical significance, but it's certainly something in the data. So let me summarize. So I'm more or less done. We seem to have some unexpected separation in H0 in hemispheres in CMB frame. So yeah, why I was motivated to look at H0 was because this is essentially what is going on in these lensed quasars here. Essentially, they're giving us determinations of H0. So it made sense to sort of look at those. Now, to stress that everything here should be in CMB frame, right? But still we see the separation. So in particular, type 1a do not look very FLRW. We could fight over this. We could say, oh, 2 sigma, nothing to see here. But it's giving you an orientation. One could imagine a comparison between Planck lambda CDM in an FLRW frame by construction. CMB is put in FLRW frame, and there's nothing to fight over there. And a supernova in a frame that is starting to look a little unlike FLRW may be trouble. So I think this is essentially the resolution to the H0 tension, is basically that we're not in an FLRW universe, and that there is some small, it's not very pronounced anisotropy, but extremely deep, which is essentially what Subir is finding in his results, and Dominic Schwartz has found, and various other people have found. And it needs to be checked if the late universe is isotropic or anisotropic before we can even discuss Hubble tension. So what I would say to the community, if you have access to some data, even if it's very low, let's say 100, 200 observables, it makes sense to sort of split them and just check, is H0 higher in the direction, in the CMB dipole direction, or not? Because I think if it's higher, then it could be consistent with what these CMB dipole people have been saying. Okay, so on that, I'm just going to finish and take questions. Thanks.
Okay, thanks a lot, Eoin, for this for showing us this very intriguing.
He's very honest, very honest.
So Armand has one question, please.
Okay.
Armin, yeah.
So I want to basically give some review of what has happened. I mean, I think Owen discussed about some works, but very selectively. Cook and Lindenberg results were refuted very quickly after what they wrote. And there have been very extensive analysis on studying the isotropy of the universe using supernova data. I mean, including what I did with Stephen Appleby many years ago. And there are many papers. I mean, the first method of this was I basically made for the Subir and his collaborators.
Right.
So one thing is that, in most of those works, people claim that they find some anisotropy. They don't consider large scale velocity perturbations in the mock data. So they just simulate the data or shuffle the data, and they don't understand that the simulated data also one needs to consider this velocity perturbations at the level of linear perturbation. And if you do that, this is the work which I did with Stephen Appleby, and I think one of the students of the.
But Armin, you were working at low Z, right? You were basically working with nearby supernovae.
We have no low Z. I mean, you can look at the paper. It's a tomography, low Z to high Z. There are massive works going on.
Okay. Just to back up a bit, you have an earlier paper with Subir, which is basically extremely low Z.
And with
up
Subir,
to
I had a problem with the interpretation, right? So that's
and it's residuals you're looking at, right? You're looking at residuals, and the conclusion was that there's some.
No, I'm not talking about that paper. First of all, that paper was the one approach, and then there is a paper 2015, I think, with the Stephen. You can ask him. I can put the link. It's
there's a paper with nearby supernovae in the title. Is it that paper or not?
Well, but you look at the paper. There are 3 papers. There are 3 papers. If you read the papers, you see that
I've read 2 of them.
So anyway, my point is that
not the
dealing with the quasars or supernova, linear perturbations are important when one makes the mock data. If you don't do that, you get the p-values of the strange values, and then one can claim that I found an isotropy. Again, isotropy is an important issue. Okay, we found it in the CMB. I think is one of the unsolved problems. But let's do proper statistics before making strong claims. And this is what I tell Subir always. I mean, because Subir sometimes find interesting things, and people find him, even may not read him. He's a great physicist, but yeah, I mean, we have to be very careful to make strong claims. That's my point.
Okay. I mean, let me just, we're on the same page on some level, right? So there is a paper from 2018, published in ANA by Subir et al., which basically imposes a dipole, works in heliocentric frame, and claims they have evidence at 4 sigma for an anisotropy, right? I have problems with that paper, right? So I think, and it's not the problems that some people would imagine, it's slightly different problems. I don't believe that you can make a statement about supernovae below Z equals 0.1. You can't infer anything about a dipole from supernovae. It's extremely difficult. You may be able to look at the residuals, and I think that was in the earlier paper, Armin, your earlier paper with Subir. But yeah, I'm a little confused by why we're seeing a particular direction.
Again, if you consider...
We're working at very high Z. We're working at high Z. Now, Armin, do you have a comment for why this would be happening at high Z, beyond Z?
This is not significant. That's my point. The direction...
I agree, it's not significant. It's less than 2 sigma.
That means nothing, right? I mean,
I agree.
direction you can find, but how significant that direction is?
You know, it's like one chance out of 100, or maybe one chance out of 20. So it's not, they're not very significant at the moment.
Okay, I'm sorry, but we are running.
Sorry, yeah.
Does anybody else have a
time,
question? Right, because statistics.
Yeah, please. We should proceed with the next speaker.
Okay, thanks for this question.
You can continue with the discussion later on. So next speaker is Javier de Cruz Perez. Yeah, please, Javier, share your screen.
I need to stop sharing. Let me go.
Yeah.
Okay. Perfect. Our next speaker is Javier de Cruz Perez, and he will talk about Brans-Dicke Lxcdm and running vacuum models, theoretical background, and current observational status. Thanks, Javier.
Okay, so hello everyone and good morning. First of all, I would like to thank the organizers, Joan and Adria, for giving me the opportunity to make this presentation. So today we are going to talk about, well, first about the Brans-Dicke model, which is known to be the first historical attempt to extend general relativity in order to incorporate variations in the Newtonian coupling. We will say something about the possible connection with the running vacuum models, which, remember, are characterized by having a time-evolving vacuum energy density, whose expression can be motivated in the context of quantum field theory in curved space-time. The content that I'm going to talk about can be found in these references, so please check them for more details. The presentation is structured as follows. First, we will talk about the theoretical background of the Brans-Dicke model. Right after, we will talk about the aforementioned connection with the running vacuum models, and we take advantage of this to also present the most important features of these models. In the fourth section, we will briefly mention the cosmological data employed in this analysis and the obtained numerical results. I will finish just by presenting the conclusions. So let's move on to the first point. For those who are not familiar with the Brans-Dicke theory, here are listed its main characteristics. We can say that the main difference with respect to the general relativity is that gravity is not only mediated by the metric tensor, but also by a scalar field. This scalar field replaces the constant Newtonian coupling. The theory also contains an extra dimensionless parameter, which is omega Brans-Dicke, and general relativity can be retrieved in this limit. The action of the model is the following one. As we can see, the scalar field is minimally coupled to the curvature. This is the kinetic term, which is proportional to the dimensionless parameter, and this piece of here contains the contribution of the different matter fields. It is important to note the presence of the cosmological term, which it doesn't appear in the original formulation. There are several ways to introduce the cosmological term in the Brans-Dicke framework. Please check the reference before mentioned to know the details, but here we just assume that, well, we associate it with a vacuum fluid, which means that its equation of a state parameter is strictly equal to -1, and that it is not coupled to the scalar field. If we vary the action with respect to the metric, we obtain the following modified field equations. Whereas if the variation is performed with respect to the scalar field, we obtain this wave equation where this term of here is the trace of the energy momentum tensor. If we choose the spatially flat 3mm Robertson-Walker metric as our background metric, we can obtain the following cosmological equation at the background level, of course, where these definitions have been used for convenience. From now on, when we talk about the usual Lxcdm, we denote it with GR Lxcdm, whereas when the Brans-Dicke framework is the one considered, we will say the BD Lxcdm. These terms out here are the total energy density and pressure for the different species, and the first term contains the contribution from dark matter and baryons. As it can be seen, the local energy conservation equation takes exactly the same form than in the Lxcdm model, and the reason of that is because the scalar field is not coupled to matter. So, well, no study of a cosmological model can be complete if we do not take it into account the perturbations. As usual, we introduce a tiny perturbation in the metric and also in the energy density and pressure of the different species in game. But in the case of the Lxcdm model, we need also to consider a small deviation with respect to the background value of the scalar field. At deep superhorizon scales, we end up with the following differential equation for the matter density contrast, where it is possible to define the following effective Newtonian coupling. Okay, so as we will see later on when I present the numerical results, the evolution of the Brans-Dicke scalar field is very slow throughout the cosmic history. So, as an approximation, we can consider that from the matter-dominated epoch to the present time, the evolution of this scalar field is represented by this expression, where epsilon is a small parameter, but it cannot be directly identified with the epsilon Brans-Dicke that I have presented previously. So if we plug these ansatz in the cosmological equation, we get the following modified Friedmann and accelerated equation, where please note that the cosmological term is no longer a constant, but a dynamical quantity. The expression for the dark energy density is this one. And what is interesting about that is this is exactly the same expression that we consider for the running vacuum models, as we are about to see. The dynamics of this dark energy component is controlled by this dimensionless parameter called mu effective. It is possible also to define an effective equation of a state parameter where this parameter shows quintessence or phantom behavior depending on the value of the mu effective. Okay, so now it is time to talk about the running vacuum models. For these models, the quantum effects coming from the matter field triggers the dynamic of the vacuum energy density. Here, mu represents the energy scale, and since we are dealing with the vacuum energy density in the cosmological domain, it is reasonable to associate this term with the expansion of the universe. By doing so and cutting the series at this order, since the other terms are not relevant for the present universe, we can obtain the following expression for the vacuum energy density. With this term of here is a constant, and nu and nu tilde are dimensionless parameters that can be related with the beta function of the running of the vacuum. Since we are not interested in having two extra degrees of freedom, we impose a relation between them. This lets us to express the vacuum energy density in terms of the Ricci scalar in the Friedmann-Lemaitre-Robertson-Walker method. This turns out to be very convenient since the contribution of the vacuum at the radiation-dominated epoch is not going to generate any conflict with the Big Bang nucleosynthesis values. As cannot be otherwise, if we want to consider this anomalous evolution for the vacuum term, we need to consider an extra ingredient. Here we consider two different scenarios. In the first one, the vacuum is in interaction with dark matter following this differential equation. If we neglect the contribution of the massive neutrinos in front of the contribution from cold dark matter and baryon, it is possible to obtain the following analytical expressions for the energy densities of dark matter and vacuum. where this definition has been used in the expressions. Of course, if we impose that nu is equal to 0, we recover the Lambda-CDM expressions. An alternative scenario that is interesting to consider is the following one, where the dynamics of the vacuum is very recent. This means that we keep deactivated the interaction between dark matter and the vacuum energy density for most of the cosmic history until the present time, when the effects of the vacuum term become relevant. A star represents the value of the scale factor when this activation takes place. So these are the expressions for the dark matter and vacuum energy densities before and after the activation of the interaction. This threshold scenario is particularly interesting for the type 1 model, so as to keep the canonical evolution law for matter and modify it at high redshift. On the other hand, the type 2 model, well, in the type 2 model, dark matter evolves as it does in the Lambda-CDM model. But the vacuum energy density can still evolve, provides that the gravitational coupling also evolves in a very mild way with the expansion of the universe. For this model, it is not possible to obtain analytical expressions for the vacuum energy density and the gravitational coupling, but as long as we stay close to the present time, the following approximation are quite reasonable. Allowing some dynamics in the vacuum energy density can help to alleviate the sigma-8 tension, since this variation affects in a non-trivial way the perturbation equations. Here we do not display all the details for the perturbation equations, but we just simply say that in the synchronous gauge, the equation for dark matter is modified in the following way. As I said, please check the reference for more details. Okay, so in order to test the theoretical predictions of the different models under study, we employ a very complete and robust data set composed by supernova, BAO, cosmic chronometers, CMB, and large-scale structure data. We denote this data set as our baseline, and when we include the prior on the H0 parameter from the Schutz team obtained with the cosmic distance ladder method, it will be noticed explicitly. So the results displayed in the following tables have been obtained by running the Monte Python together with class. The last one has been modified properly in order to incorporate all the features of the different models under study. We display the usual parameters, also some important derived parameters. And for the type 1 model, the extra degrees of freedom is encoded in this new effective. Whereas for the type 2 model, in addition to this new effective, we also have the initial value for the Newtonian coupling. Finally, for the Lxcdm model, we need two extra degrees of freedom, which are the epsilon Lxcdm and the initial value for the scalar field. It is important to note that for all the models, when the H0 prior is not included, the values for the sigma-8 remain in the low range, which means that they help to solve the sigma-8 tension. It is important to remark that according to the D criterion, the type 1 model with the threshold is strongly favored when it is compared to the Lambda-CDM model. So now let us have a look to the results obtained when the prior is included. as it can be clearly seen, only the type 2 model and the Brandstike model are able to easy the H0 tension. The other ones, for the other models, the value of the H0 remain as in the previous scenario. Additionally, the values of the sigma 8 parameter are still in the low range. So these models are able to alleviate both tensions at a time, which is really remarkable. This can be seen in a more graphical way by looking at the following plot. The type 2 model and the Brandstike model manifestly alleviate the H0 tension, since the contour plots are placed in the high value region for the H0, without spoiling the sigma 8 tension, which, as I said, is really remarkable. On the contrary, the type 1 model, with and without, well, with and without the threshold, cannot address the H0 tension. They do a good job in regards to the sigma 8 tension, but not in the H0 tension. So let me conclude just by presenting the obtained conclusions. The Brandstike model, even if it has a higher value of the effective Newtonian coupling, it's able to fit the different cosmological data without problems. There is a significant evidence that a dynamical vacuum energy density can improve the description of the different cosmological data in comparison to the Lxcdm model. Such dynamic helps to loosen the sigma 8 tension, as we have just seen. And finally, only the type 2 model and the Brandstike model can deal with both tensions at a time. Well, that's all I wanted to say. Thank you very much for your attention.
Okay, thank you very much, Javier, for this very interesting and detailed talk. Now it's time for questions. If there is any, please raise your hand.
If
yes,
I may,
Johan, please.
Sorry, I have a very quick question. Can you remind me why, for the Brandstike model, you do not run over the scalar spectral index? I think in your table there was no value for in the previous table. I think
in both the scenarios we have considered the spectral index as a free parameter.
Could you go to the table, to the slide before?
This one?
Yeah, here it seemed there was none. So I was wondering why there is no value in the table for NS. Maybe it's just a type, I don't know.
The NS is here.
Yeah, but for the Brandstike, like in the last column, there is no value. So I was wondering whether there's a reason.
Oh, sorry. This is a typo. Sorry.
I see. Okay.
Okay.
Thank you very much.
I know what you mean. Sorry.
No, don't worry. Okay. Thank you.
Yeah, it's a typo, but we have included in the analysis.
All right.
The value
okay. Yeah, thank you. I thought it was substituted by some of the parameter combination. Okay. Yeah, thank you.
No, thank you for pointing out.
It's in the paper.
Yes, please, Johan, you have also a question, I see.
Yeah, well, just a comment. I mean, you emphasized that that these kind of models, in particular the type 2, can solve, alleviate, or at least not to worsen any of the tensions. My question is whether you are aware of other models in the market that can do a similar job.
To the best of my knowledge, no. There are no models that can help to alleviate both tension at a time, because there are some attempts that really improve the H0 tension, but then the value of the sigma 8 is in the very high range. So to the best of my knowledge, no.
Please, Nick.
Yeah. Well, on this comment by Joan, there are no models, of course, but you haven't taken into account all the dust or other sectors in curvatures, spatial curvatures, in the FLW. This, I don't know whether the other models, what they could do under these assumptions, under your assumptions of the standard curvature, spatial curvature ups and flat universes, then yes, but the other models, I have no idea. Dust is a factor that in all this discussion on isotopies as well, they could masquerade things, in my naive opinion. So model for dust, in my opinion, I'm not expert, they are not developed yet to a satisfactory point. That's a comment, nothing. So, but I agree with your assumption. Within the assumptions that you made, flat universe is, I mean, most likely the universe is flat.
It would be interesting to study extended scenarios, including the curvature of the dust model, of course.
I have one very quick question. Sorry?
No, I just wanted to, no, please go on.
No, just to finish. In your Brans-Dicke model, there is no cosmological constant. It varies with the scalar field. Am I right? Or
no,
it's constant. Okay, fine. Yes, you mentioned that. Yes. You're great.
That's fine. It is not present in the original formulation. But we have included here.
But as a constant, that's fine. Thanks.
It is a constant, exactly.
Thank you.
Okay, thanks again, Javier. And now let's move to the next speaker, Subodip Mukherjee, who will talk about prospect of measuring Hubble constant using gravitational wave sources. Thanks.
Can you see my slides?
Yes, perfectly fine.
Thanks a lot. So thank you, organizers, for giving me the opportunity to speak here. So we heard a lot about the tensions from morning. Now I'm going to talk about how to resolve it without using the current probes which you're using in making these measurements. And as all of you know, one of such probe is gravitational waves, because it brings a very neat and clean window to measure the expansion history of the universe. So I think this has a part which all of us will agree with, different statistics and data, but all of us agree on this part that we have made quite a few developments in understanding the energy budget of the universe, as I've listed over here, nothing new. And this has really questioned our current understanding of the fundamental physics or our working principle, because in my opinion, high quality observations has led to an era of precision cosmology, which questions our current understanding of the fundamental of the basic physics we have dealt in our daily life, what we have learned from a standard model of particle physics. So we are actually far from understanding this phenomenological model, what we call as the lambda cold dark matter model, which is, and there are several open questions in the topic. We do not know what is the current expansion rate of the universe. I think that's the part we are continuously discussing today. We also do not know what is really cold dark matter, what is really dark energy, and is the general theory of relativity the correct theory of gravity? So these are quite a few open questions in the field, and one of the key aspects which we would like to explore in the future observations is to basically understand the Lxdm model and then to think about whether there are any departures from it. And gravitational wave brings a very neat window to that, as I mentioned in the beginning, that with the help of gravitational wave sources, we will be able to measure the high redshift universe with sources of very different masses, so ranging from something like a few solar mass to something like million solar masses. So here I'm showing a plot of upcoming terrestrial gravitational wave detectors such as LIGO, Cosmic Explorer, and Einstein Telescope in left. What are their redshift reach in the y-axis, and what are the masses of the sources that we are going to detect? So this solid line indicates the horizon of our detection. That means that with LIGO shown in blue, we'll be able to reach almost up to a total source mass of about 100, up to about a shift of 1.5 to 2. And with Cosmic Explorer and Einstein Telescope, the third generation gravitational wave detectors, we will be able to reach way up to almost a shift of 70 or so. Both Einstein Telescope shown in magenta and shown in green, and Cosmic Explorer shown in magenta. If you go to the other kind of sources, the supermassive binary black hole sources, which are possible to detected from space-based detectors such as LISA, we will be able to measure sources of very different masses. Now it's about a few thousands to few millions of solar masses, again up to very high redshift, which means that with now this kind of transient sources, we can now ask a couple of questions. And those are like in the how these sources we can be used to understand the physical cosmology. That's the upper part of my arrow. So how can I go from here to here and understand about the laws of physics which governs the universe? The other part, which is interesting, is with our current observations from EM sector, what can we understand about the properties of the transient sources? Like, what are the black hole masses? What are going to be the redshift distributions of these black holes? What are their typical mass distributions? And it's very important to point out that the cosmology and the source population of gravitational wave sources plays a very hand-to-hand role in actually deriving correct results. So in my today's talk, I'll be only focusing on a very like a very minor part, which is regarding the measurement of the expansion history of the universe using sources with electromagnetic counterparts and sources without electromagnetic counterpart. So the advantage of sources with electromagnetic counterpart is basically you can have an inferred the redshift independently, which is good. And the advantage for sources without electromagnetic counterpart is because you can go up to very high redshift, as is shown here by this nice diagram from Reeds et al., that we can actually reach up to very high redshift with sources such as binary black holes, and sources such as binary neutron stars. We can reach only up to very low redshift with the current detectors. And why this is very interesting is because if you see our expansion rate as a function of redshift, the all interesting physics of the transitions into dark energy sector happens at the low redshift. So if we can map this transition very nicely with gravitational wave sources, that is going to be very interesting. And also, of course, this tension which we are talking about is the value of H0 from Planck and the value of H0 from Rees et al. That has been quite a lot explored in the literature as that the early universe probes show something like around 67, and the late universe probes shows you something like of the order 70, above 70, 74. But please remember that even in the late universe probe, when you change different calibrators, you indeed get a very different results. And this is not new only for TRGBs and shoes, but also for many other teams have shown similar conclusions. So I would say that in this table has now improved significantly by this plot by Eleonora, where more data were added, but nothing changed in the conclusion wise. We are still seeing a discrepancy in the indirect probes of the early universe probe to the late universe probes. Some of the TRGB measurements tend to be more consistent with super CMB than compared to the shoes results. But today I am going to talk about this part, which is about the gravitational wave measurement, the lower panel. So let's at first talk about sources with electromagnetic counterpart. That is like the binary neutron star sources. So the interesting part is with gravitational wave sources, we can measure Hubble constant. And this is first time shown by Bernard Schulz in 1986, that the luminosity distance inferred from the strain of gravitational waves, and if there's an electromagnetic counterpart independently measured, then the ratio of both of them can give you a value of Hubble constant if one can correct for the peculiar velocity. And indeed, this is what we do in the LIGO collaboration, and we have measured for the first time such a bright standard siren like GW170817, and we have inferred the value of H0 shown in this blue line, and in green and brown we are showing the curves from Planck and Schulz. Though these measurements are currently not very comparative with the other bounds, but this is a very promising window. So one of the passing comment by Jon in his talk was that about the peculiar velocity corrections to the gravitational wave sources. Indeed, this is the very important part, and we take care of it very properly in our analysis. So here we show how the peculiar velocity correction can be made to the gravitational wave sources. So I am showing you a local map. We have estimated using a full Bayesian reconstruction of the peculiar velocity from large scale structure observations. And here you are seeing a corresponding map of that. And as a result, at any location, if you can infer the gravitational wave source there, you can go and correct for the peculiar velocity from this map, including the full posterior on the peculiar velocity. So we do that in our analysis, and we have shown that GW170817 result of LIGO-Virgo collaboration is very robust. As you can see, the results from the red line is with the previous peculiar velocity corrections. The black line is from our method. But when you include the results from the VLBI observation of the jet measurement, you significantly improve the H0 measurement for GW170817. So your error budget in luminosity distance reduces, and then the error budget in peculiar velocity plays a significant role. And as a result, you see a significant a bit of deviation of the value of H0 inferred jointly from GW plus VLBI case. So that's the blue curve we should point to see now, which that's now consistent with the Planck results about 68 km per second per megaparsec. So the take-home message here from this plot, you should see that peculiar velocity indeed can affect both mean and the error bar of the measurement of Hubble constant, and these are taken care very properly currently in the analysis. There is a new catalog under preparation by Dalia et al., which is for the multi-messenger data analysis, and it takes care of the peculiar velocity corrections. So when you do so, you can now ask how many sources of binary neutron stars do you need to measure Hubble constant? And this is the prediction from Chen et al., who have shown that we need about 50 gravitational wave sources with electromagnetic counterparts such as binary neutron stars to measure a Hubble constant of the order of 2%. So as of now, we have only one source with electromagnetic counterpart. So that you should not take this year very seriously anymore, but these are with the rates which were that time proposed. But as of now, we have only one source, but this is definitely a very promising window to measure Hubble constant. But what about sources without electromagnetic counterpart? As I already told you, for these sources, we can see further out. So because of the volume factor, we can see more objects. And because we are able to reach higher redshift, we can do cosmology beyond H0. So let me tell you what to do with those bunch of black holes which we are detecting. Remember, with O3A, we have about 50 gravitational wave sources we have detected, out of which 49 are dark sirens or without electromagnetic counterparts, and only one is a bright standard siren. So let's now talk about those dark sirens, which are sources without electromagnetic counterpart. So if I tell you, give you a bunch of gravitational wave sources in the sky, and I ask you how they're spatially distributed, they are not going to be distributed spatially randomly, but they're going to follow the underlying matter distribution. So here you're seeing a simulation from Illustris of these dark regions at the places where I have galaxies or clusters, and the whitish regions are the places where I have voids. So intrinsically, you expect the gravitational wave sources to be going off at the places where I have galaxies. So can we use this aspect to infer the redshift of the gravitational wave sources? And what is one of the important ingredients to do that is to understand how gravitational wave sources are going to trace the underlying dark matter distribution, what we call as the gravitational wave bias parameter and its redshift evolution. So what I'm going to introduce you now is that one can do a new method called a cross correlation of the gravitational wave sources with galaxies, the spectroscopic galaxies. For this analysis, we have taken spectroscopic galaxies. So which is basically the estimation of the how much excess probability of finding galaxies around a gravitational wave source in comparison to a random distribution. So as I already told you before, that gravitational wave sources are very good distance tracers. So let's say I observe them in a particular sky direction in a luminosity distance space. And in the same sky patch, I have measured galaxies spectroscopically for this example, but it's not limited to that. It can be also applied to photometric redshift measurements. I have measured galaxies. So what I now do, I take redshift beams of in the galaxy sector, and I take a fixed tomographic luminosity distance bin, and I calculate this particular quantity, which I call the cross correlation of the gravitational wave sources and galaxies, where the xi of r is the key, is the clustering information between the gravitational sector and the galaxy sector. And we would like to maximize this clustering probability, or hence the probability of dp. Of finding it. That's good, yeah. So then what we do, we take a redshift bin, we calculate the value of dp, we go to the next one, we again calculate the value of dp. You can see it is consistent with 0 here. We go to the next one, you see a slightly higher value of dp. So that means this particular redshift shows more clustering with these gravitational sources. You go to the next one, is again shows something consistent with 0, and next one consistent with 0. This implies that you have associated this redshift bin with these gravitational sources as by clustering method. You can do that for different tomographic bin of the gravitational sources, and you can correspondingly identify different tomographic bin of redshifts from the galaxy survey. You combine both of them, and you can find the expansion history parameters such as H0, omega m, and dark energy from gravitational sources, even if they do not have electromagnetic counterpart. And here is a result from this cross correlation technique for LIGO-Virgo-Kagura network of detectors with spectroscopic surface of galaxy surfaces after marginalizing over matter distribution and bias parameter for sources distributed up to 0.5. With 50 gravitational sources, one can get to something like 3% measurement of H0, about 3.5. And with about 200 gravitational sources, we can get to 2% measurement of the value of H0, which will be sufficient to basically resolve the tension between Planck and shoes. And interestingly, this method is not only limited to H0 measurement, but it can also shed light on the dark energy properties. I'm showing here that one can get to a measurement of about 3% measurement of dark energy equation of state by this technique, and also measure the gravitational wave bias parameter, which you have no idea right now what its value is, like how GW sources traces dark matter distribution. And these are the quantities we will be able to measure from gravitational sources.
1 minute.
So, yep. So in summary, I will tell that with gravitational sources, we can map the low redshift universe right now. And in future, we can go up to high redshift with LISA, Cosmic Explorer, and Einstein Telescope. And these are all possible because of an immense amount of observations coming from large scale structure and gravitational sector both. So I will say this is really a golden era of multi-messenger cosmology. So these are my take-home messages from my talk is gravitational sources will be able to provide an independent measurement of the expansion history of the universe, how we can be able to measure gravitational sources, how it traces the underlying dark matter distribution. By cross correlation, we'll be able to reach both precision and accuracy up to very high redshift. And nevertheless, this method is also applicable to upcoming detectors such as Cosmic Explorer and Einstein Telescope. So I will say the tension which you're talking about will be very soon can be resolved from a very independent window such as gravitational waves. So with this, I'll take questions. Thank you very much.
Okay, thanks a lot, Subodip, for telling us about these very promising prospects. Yes, there is a question by Arman.
Okay, so the very nice talk, very interesting way to correlate basically the dark Siren information and the large-scale structure data. But one thing about the precision of the Hubble parameter, which you mentioned using these dark Sirens. So there should be a model assumption, right?
Model assumption of what?
I mean, you need the background cosmology assumption, right? I mean, if you don't know the background cosmology, only at a very low redshift, you can get the H0 from the Sirens. If you go to redshift behind 0.05 or 0.08, then you need to know the background expansion.
Without of course, that, and we do that in our analysis. So these analyses are obtained after marginalizing over H0, omega. H0 is obtained by marginalizing over omega matter, dark energy equation of state.
So, but you assume the equation of a state. You assume
yes,
the
but that is not a limitation. One can take W0, WA parameterization or any other parameterization.
So my point is that still your estimation will be depends on the choice of parametric form which you are considering.
Estimation will not be dependent. These results are. Because in these results, I have taken a particular fixed model. But if you're talking about the technique, that
for example, technique is great. I have no problem with that. Yeah. But I'm saying that let's say this 2% which you are talking about. Here, what is the dark energy model you assumed? Is it W?
So here it is lambda.
Okay, it's lambda CDM.
So here you can see this, that here I'm considering W0 as a free parameter and H0, along with gravitational bias parameters. I have also similar plots for other cases. You can see in my papers.
And then what would be the precision for H0 if you assume W to vary?
Oh, it is at the very similar level. You can see here that H6 we can measure to sub% accuracy, or with about 2% accuracy of value of H0. So
you assume the constant W.
Yeah, that's right, constant W. Even for WA, you can do the similar. The reason is very simple, because we do a tomographic binning of the DL estimates. So the low redshift,
I understand that. Yeah, I understand that. My whole point was that, still when we go to the dark series, we need to know the background expansion. The point of the Holtz et al. Mainly was that when we deal only with the neutrino star mergers, we don't need to know the background expansion. This is great. I mean, this is exactly a very nice way
no,
to
but I do not agree with that statement, because there is, you always need to, if you are inferring a limited amount of cosmological parameters, you need to definitely choose a model. There, you can combine that's always the case. I can measure here to any number of independent parameters you can come up with, but that will not limit the analysis technique, because
sure. I mean, again, I have no problem with the technique.
Yeah.
I'm saying that you can still combine with other information to have a non-parametric or model independent estimation, right? So this is something.
Sure. I can get to a non-parametric measurement from gravitational sources as well. But that is a paradigm of cosmological analysis. That's
okay, let's talk later about that. Yeah.
Okay, very good. I cannot see more questions. So thanks again, Subodip. And let's move to the next speaker, Cristian Moreno Pulido, who will talk about renormalized vacuum energy density without m to the 4 terms. Thanks, Cristian. So, okay.
Sorry, let me just. Okay, good morning. First of all, thank you for inviting me to this nice meeting. I'm going to talk about normalized vacuum energy density without m to the 4th terms. This talk is a way to motivate a family of models called running vacuum models. For instance, the models that Javier was talking about before, and also through this quantum field theory computation that we are going to do, we will see that we avoid some of the most problems about the vacuum energy, which is the contribution of the 0-point energy terms, which contributes with the fourth power of the mass, sorry, to this quantity. So let me just. Okay. So this is the outline of the talk. First, we will comment briefly the cosmological constant problems. Then we will try to go beyond and talk about dynamical vacuum energy. And after this, I will try to explain the model the computation that we are considering and see how we can renormalize this vacuum energy density. So, as you know, observations tells us that the universe is expanding in an accelerating way due to an entity which we commonly call dark energy. This dark energy is usually related with the mathematical term in Einstein's equation, which is the cosmological constant lambda, and may be related with the vacuum energy density associated to quantum fields. An important issue is that the observations tells us that the value of this energy density is of the order of 10 to the minus 47 GeV to the 4. Meanwhile, if you compare this value with, for instance, the 0-point energy for the electron, we see a 34 orders of magnitude of difference. Additionally, there is another issue with the vacuum energy density, which is the fact that at the present time, it has the same order of magnitude as the energy density associated to cold dark matter. And this is strange because the lambda, the cosmological constant, is assumed to be constant. Meanwhile, the cold dark matter is assumed to decrease with time, the energy density. We're going to work in a Feynman lemaitre Rosen Walker space-time, considering flat space and with this metric. Sorry. Okay. But we can go beyond. We can consider the cosmological principle led us to promote the cosmological constant to a function of the cosmic time, or even we can consider a dynamical variable chi that depends on time. So as Javier has shown before, this kind of things may provide a better phenomenological account of cosmological observations and tensions. For instance, the running vacuum model is one of these models that proposes a parameterization of the vacuum energy density as follows, with this term proportional to the second power of the Hubble function. Some analysis of these kinds of models indicate that this parameter nu is small, as it has to be, because at the end of the day, we cannot make a big departure from the Lxcdm. But this is not the only example. We have seen that Javier proposed one with the scalar Ricci instead of the Hubble function. So there are more possibilities. For instance, consider bigger powers of H and its derivative, or even consider the variation of other coupling constants. So more specifically, Rolanda in the effective action of quantum theory is considered to be a coupling which evolves with the normalization scale that I put M here. And in the cosmological context, we could consider that this normalization scale could be something related with evolution of the universe. For instance, the Hubble function that is a scalar, but maybe the temperature or something else. So we start with the Einstein's equations. Here we have put a cosmological constant, and in the matter part, for simplicity, we are just considering one real scalar field with this action. As we see, we have implemented a non-minimal coupling with the semi-classical gravity through this parameter Xi. And what we are going to do is to split this field in its background part, its classical part, and its quantum part in these quantum fluctuations, which can be written through this Fourier integral in this decomposition of modes. So following this prescription, we can also consider the energy momentum tensor associated to this scalar field to be split in a classical part and in a part associated to the quantum fluctuations. So we can postulate the vacuum energy, the energy momentum tensor associated to the vacuum energy to be this sum of two contributions, one, the cosmological constant, and the other, the energy momentum tensor associated to the quantum fluctuations. At the end, we will assume that the vacuum energy density is proportional to the 0,0 component of this tensor. So the usual commutation relations led us to rewrite the Klein-Gordon equation for the quantum fluctuations in a differential equation for the modes. Here we have defined this omega square in this way, including the Ricci scalar. This equation has been solved in classical books, in articles, and the solution proposed is that one that I put here in equation 8, where this capital WK is the solution of this nonlinear differential equation that I put at the end. This differential equation, unfortunately, cannot be solved analytically, so we have to present some way to solve it. And this way is what we call the adiabatic regularization. This kind of solution is valid when you have an almost static background, that is that geometry does not evolve very quickly with time, so that you have a very slow function, omega k, and you can use an adiabatic series in order to solve the differential equation. So this series is called also WKB solution, and is organized in different orders, different adiabatic orders, in which the first one, it's the order 0, is corresponding to the momenta, to the mass square, and also the scalar factor. Of order one would be for first derivative in time, such as the first derivative of the scale factor and h. Of second order for the second derivative of a, the product of the derivative of a by itself, derivative of the Hubble function, etc. So we can sum up this by saying that each additional derivative increases the adiabatic order by 1 unit. And by doing this, we propose that the solution will take this form as a sum of different terms of even adiabatic order. This is justified by means of general covariance. So the first term that we propose is that one, this omega k, this free energy, but we are considering this M, this capital M, to be an arbitrary mass scale. That is, we're replacing the mass of the scale factor by this arbitrary mass. Also, we define this delta square to be another a parameter of adiabatic order 2, and it's useful for normalization purposes. So the next orders are obtained by iteration. That means that we take the zero order solution, we reintroduce it in the differential equation, and we solve for the second order. Once we have the second order, we introduce again the solution and find for the fourth order, etc., etc. So with this procedure, we are able to compute the energy momentum tensor, in particular the 0,0 component, up to the fourth adiabatic order, associated to the quantum fluctuations of the scalar field. And the result is this little monster. The important part that I want to remark here is that the terms in red are terms that are manifestly divergent. That is that the integral goes as 1 over k or worse. So, so this integral has these divergent terms, and the other part is perfectly finite. For this reason, we do this split in a divergent part and a non-divergent part. So the reason that we compute the energy momentum tensors up to fourth adiabatic order is due to that the divergences are present just up to this order. So now we have localized the divergences. It's time to define our renormalization program, and the one that we're going to consider is that one in which we compute the energy momentum on shell and do a subtraction of the fourth adiabatic for the four first adiabatic order terms of the energy momentum tensor, but at the scale at the arbitrary scale m. If we do this prescription, we end up with this solution for the renormalized energy momentum tensor. And as we see, the terms proportional to the m to the fourth powers that I commented at the beginning are present. Of course, if we put m equal to the mass of the scalar field, this vanishes because of the definition of renormalization we did. An important thing is that even if they wasn't present at the beginning, some high order terms are generated by quantum fluctuations, and the Einstein equation is updated to have this extra term here in Freeman-Lemaitre Robertson-Walker. And what we have to do now, in order to avoid this m to the fourth term that we have encountered, is to define this subtraction of two different scales, namely this m and m0. And if we do that, we can parameterize this difference by these f functions, which are just simply the difference of couplings at the different scales. So that by comparing the expressions we have found, we were able to find the value of these f functions. And as we see, this m to the fourth power is associated to the function of the difference of energy densities of the cosmological constant. But if we remember the definition of the vacuum energy that we have proposed, is that one that is the vacuum energy density, is not only the cosmological constant, but also the energy momentum tensor of vacuum of quantum fluctuations contributes. If we do this, if we compute this expression, we end up with this final expression for the vacuum energy density once we do the difference between the two different scales. That is, we are comparing m with the value of m0. The way that we have to interpret this equation is that we are provided for some value of the vacuum energy at some scale m0, then we are able to compute the running at other scale. So we can apply this formula, for instance, for m0 equal to mx, where mx is the typical energy scale of relatively unified theories. And for instance, we can put m to be equal to x8 which is the value of the Hubble parameter at today's day. And by doing this, if we neglect for the present universe the terms going as fourth power of the Hubble function or terms of adiabatic order 4, we can end up with this relation between the two different scales, where we see that this small parameter, nu effective, appears defined in this way. Let me say something. The sign of this parameter is not only determined by this psi, because we have to take into account that at the end we want to generalize this method for more fields, and all of them will contribute to this effective parameter. So at the end, we have to compare with data. More generically speaking, if we consider an arbitrary Hubble function, we can relate it with the Hubble function at the present time with this nice formula, this for late universe. And if we compare this with the fourth example that we show, that I have shown at the beginning, we can recognize this running vacuum model behavior. Just to finish, let me tell you that there are more general expressions for the energy momentum tensor for the vacuum. Instead of just considering being proportional to the vacuum energy, we can consider a more complex tensorial structure here. For instance, by including these couplings alpha 1 and alpha 2 coupled to the Ricci scalar and the Ricci tensor. And what we are left when we do this and following similar computations as we did before is that the vacuum energy density associated to the Hubble function, it adds up a new term which is proportional to the derivative of the Hubble function and not only to the second power of the Hubble function. Here again, this nu effective 1 and nu effective 2 are proportional to this ratio of scales. And by doing this, we can consider more different models. And for this reason, I was talking about a family of models.
2 minutes, Christian.
Okay, thank you. So just to conclude, we have seen that the normalization value of vacuum energy density at some scale m has been obtained from this quantum field theory calculation instead of other more generic arguments such as the normalization group. We have avoided this m to the fourth power by considering the difference between two different scales. And as I commented, we can obtain a richer phenomenology if we consider a more complex relation between the vacuum energy density and the 0,0 component of the energy momentum tensor associated to the vacuum. For instance, as we've seen, we can make appear this derivative of h. One thing that would be interesting is to see if we can generalize these results to other fields such as fermions and see the behaviors of the different terms in that case. So thank you for your attention. And if you have any question.
Okay, thank you very much, Christian, for this very nice talk. And now, yes, it's time for questions. Please raise your hand. Okay, Joan.
Yes, Christian, thank you for the talk. I think it would be interesting that you comment on the possibility that this model has something to say about inflation, especially in connection to the higher order terms that you have mentioned, just in passing. You could perhaps comment more on them.
Okay, thanks for the question. That's true. As I commented here, this series was cut up to the second adiabatic order because we were considering the result for the late universe. And as we know, this value of H naught is small at the present. So if we, instead of cutting this term, we consider bigger powers, for instance, actually, I should have put here some dots because this can continue up to more adiabatic orders. But here we have this fourth adiabatic order in which we see the derivative of h to the square and more terms. And in that case, this could be similar to Starobinsky inflation, in which it's triggered by the derivative of h, but more in general, for instance, by considering other fields or even interactions, we may see that here they would appear more terms that, for instance, the h to the fourth power, or even if we consider bigger orders, it is possible to obtain terms such as the h to the sixth power over a mass scale. So these terms, within the context of running vacuum energy models, can be seen as triggering the inflation, because as we know, the Hubble function in the past takes a very big value, and in particular during inflation, they can represent this high vacuum energy density, which triggers inflation, and later on decays after reheating. So it's a possibility that we have to study by considering these terms proportional to bigger powers of H, but unfortunately we have not done at the moment. But yes, this model, this kind of models has the potential to also study the early universe once one consider more adiabatic orders. Exactly.
Okay, Christian. Okay, sorry. We have run out of time, Joan, but if you want to make a comment.
Absolutely. No, I mean,
okay.
It is fine. Just to mention that, as Nick has shown in the beginning, in fact, despite the fact that this quantum field theoretical calculation does not provide the h to the fourth power in this framework, it can be obtained in a stringy framework. But as you mentioned, these dots that you didn't mention here, which correspond to the sixth adiabatic order, they may have some surprises for us, which we are computing. So we will know soon. Thank you.
Very good. Thanks a lot, Christian. And now it's time for our last speaker today, Mariam Agae, who will talk about particles and H naught tension in the late-time universe. So please, Mariam, if you can share your screen. Please. Okay, I see you now. Okay.
Hello.
Hi.
Let's see. I'm going to speak about particles and their role in alleviation H naught tension at late time universe. Actually, H0 tension is a significant lambda CDM challenge, and it's a member of large family of lambda CDM challenges, which includes missing satellites, speed of structure formation, angular momentum of baryons, cosmological constant problem, and recently H0 tension. H0 tension arises from two distinct values of H0 measured using CMB and local observatories. The first one gives a number around 68, and the second one gives 74. And there are recently some ideas of more possible distinct values for H0 with cosmological origin. These problems and challenges made people to think about some alternatives for lambda CDM or some modifications for that. One of the candidates that can be a modification or replacement for lambda CDM is unparticles, a concept in particle physics. Unparticles are the low energy phase of Banks-Zaks field, and they first introduced by Georgi in 2007. They are defined by an energy scale, as you can see here. Let me use the pointer. At very high energy scales, above MU, there are Banks-Zaks field, and they can interact with standard model particles. Below these energy scales, their interaction will suppress, and as the energy scale decreases to lambda U, the scale invariant feature of Banks-Zaks field appears, and their new phase as unparticles arises, and they can interact with standard model particles with a small coupling. So their main feature is that they belong to energy scales below lambda U. They can interact with standard model particles, and they have a scale invariant feature at low energies, and they have a non-trivial IR fixed point, which is where their scale invariant feature arises. These properties will make them a candidate to alleviate H0 tension because of their dependency to an energy scale. With these properties, we can see that for theta mu nu as energy momentum tensor, we can introduce the trace anomaly of energy momentum tensor as this expression. Beta is beta function, and this equation secures that it has a non-trivial IR fixed point. And as we are looking for the first correction to the conformal limit, the normal product of F mu nu will be equal to this expression, B times T to the power of 4 plus gamma, where gamma is anomalous dimension, and the thermal average of energy momentum tensor is equal to energy density minus 3 times P of unparticles. These equations gives us these three expressions. Delta is equal to A plus gamma, and in the other hand, delta is defined by dimensional by du, which is the scaling dimension of the operator of unparticles. This parameter cannot be negative because negative scaling dimension is equal to the violation of unitarity, but there are some papers with negative du. Usually they take du to be between 1 and 2 here, and in our work we cover all over the range from negative to positive du. So we have delta from -6 to 1, and delta equal to -2 is equivalent to du equal to 0, the boundary. Using this expression with first thermodynamic law, we have the pressure and energy density of unparticles as these two expressions. As you can see, delta equal to -2 is the holographic limit of these unparticles, and in the absence of A, we will go back to usual radiation. This pressure and energy density will end up to the first Friedmann equation to be like here. We have added unparticles to the usual radiation, matter, and cosmological constant. And as we are going to investigate late-time universe, we can ignore the radiation part easily, and the energy densities can be calculated from conservation equations for each part to be like this. So we have the exact expression to be like here, a term for matter, a term for particles, and cosmological constant. And we have three flat conditions. In comparison with lambda CDM, we can see that there is an extra term, which delta has the main role in it. And this delta term will make the theory a bit different from lambda CDM. As we are going to see what happens to H0 at late time universe, let's see the evolution of Hubble parameter at high redshifts and low redshifts. At high redshifts, which means around BNS, lambda CDM behaves like this one, H0 times z to the power of 3/2. But for unparticle cosmology, it's a bit different. For delta less than -3, the behavior is exactly the same as lambda CDM. But for delta larger than -3, it's different. This means that unparticle cosmology with delta larger than -3 cannot be anchored with lambda CDM and many other gravitational theories at BNS. This is a problem for unparticle cosmology, but as we are going to investigate late-time universe, we will leave it for the moment. At low redshifts, which means late-time universe, lambda CDM behaves just like this equation, the Hubble parameter of lambda CDM. Let's note that the coefficient of z here is always positive, but for unparticle, it's different, and the coefficient can be positive or negative for different values of delta. These the different behaviors at high redshifts and low redshifts made us to introduce three general possibilities for the evolution and destination of Hubble parameter. As you can see, there are three classes, class A, B, and C. Class C defines a Hubble parameter which goes to 0 at a distant future. This means a Minkowski spacetime. Class B defines a class of a Hubble parameter which goes to constant at distant future, which means a stable de Sitter phase for the future of the universe. But class A is different, and Hubble parameter will blow up in a future, maybe a close future or distant future. And an inevitable result of this evolution is the existence of the turning point. The important point for these three classes is that the future behavior of Hubble parameter has its own footprint on the current value of H0. As you can see, for class A, the value of H0 is larger than class B and C. And our universe will choose only one of these scenarios. So any proposed gravitational theory should satisfy the choice of nature. For lambda CDM, the first derivative of a Hubble parameter at z equal to 0 is 1/2 times H0, which means that it's always positive. So lambda CDM will see it in class B or C, but for unparticle, it's different, and it can have negative slopes at z equal to 0. So maybe unparticle can satisfy class A. But let's see what happens in confrontation with data. For doing a confrontation with data, we need some prerequisites. Here we are going to use a model independent polynomial fit for our analysis. So this polynomial fit will behave such as a truncated Taylor series of our model. So we need to know the radius of convergence for our model. The radius of convergence is defined by the closest distance from a pivot point to a singularity or branch point. As you know, for lambda CDM, it's like this, and radius of convergence is around 1.3. But for unparticle cosmology, for Z naught equal to 0, radius of convergence is 1.3, and the branch points are, as you can see in this figure. The important point is that the value of RC is related to the position of pivot points. So if we choose Z naught to be equal to 1, the value of RC will be different. And for unparticle, the value of RC depends on the value of delta, but it basically remains around 1.3. Having these, we do our confrontation. The data set that we are going to use is the data set provided by Farouk and his co-authors. Doing a polynomial fit to the data, we can get this curve. And if we extrapolate it to the negative Z, to the future, we can see that the data are happy with the existence of a turning point, an unstable de Sitter phase for the future of the universe. And if we add our models here, Lxcdm and unparticle, we can see that they are different. Although unparticle cosmology can suggest a higher value for H naught at Z equal to 0, it tends to go to a constant in the future, and it will not follow this curve here. If we zoom in, we can see that there is a deviation here at Z equal to 0.07. So it's less likely for unparticle to alleviate H naught tension, but we will go a step further. At this point, the interesting point is that delta equal to minus 2.03 is the selection of data for the value of delta. So the holographic limit is essentially the natural choice. And we can see that it remains for different values of Z max in next figures. Here, for our next step, we try to present a QQ diagram to see if really unparticle cosmology can alleviate H naught tension or not. Q is deceleration parameter, and capital Q is its first derivative with respect to Z. As you can see, polynomial fit of data to data gives higher values for capital Q. And for unparticle and Lxcdm, they have similar behaviors, and they cannot follow the trend of
3 minutes,
data.
Mariam. 3 minutes.
Okay.
Okay.
But for delta, we can see that for different values of Z max, delta is around -2. So we can say that H naught tension cannot be alleviated. And for this figure, we can see that with different values of delta, only for the values which violates unitarity, we can have some alleviations. So unparticles are ruled out for H naught tension alleviation. So the final conclusions that we can have is that unparticle cosmology cannot alleviate H naught tension because of evident gap between the curves of polynomial fit and unparticle cosmology in QQ diagram, and deviation from polynomial fit in Hubble diagram, but unexpected appearance of holographic limit at delta equal to -2.3 as the best fit of the model gives more credit to holographic dark energy, and the trend of polynomial fit suggests the existence of a turning point in Hubble evolution, which means unstable de Sitter phase as at late time universe, and the conjecture that you can take home with yourself and we with ourselves is that there is a necessity for looking for a holographic dark energy model with late time unstable de Sitter phase, indicating the presence of a Hubble turning point. Thank you.
Thanks a lot, Mariam, for this nice presentation. So now it's time for questions. Okay, I cannot see any. Perhaps I can ask, maybe it's a very naive one, but in the first slide, you told that you have said that one of the tensions is the angular momentum of baryons, but I don't know what is this tension. What is this tension? Maybe you could comment on that.
The angular momentum of the baryons?
Yeah.
This is the difference between the predictions of lambda CDM for them and what is observed. They are a bit large. Sorry, they are a bit larger.
Okay, but you mean large scale structures or something, or?
Sorry?
You're referring to large scale structures, or?
No. Here, you mean?
Yes.
No, it's not for larger scale structure.
Okay. So, okay, I had never heard this, but I don't know if there are more questions. So, and particles could not play the role of dark matter, right?
No,
okay.
We can rule them out.
And
but they are still useful.
But can you go to the second slide, please?
Sorry?
Can you go to the second slide, please, in your presentation?
This one?
Yeah, so you've mentioned that below a given energy threshold, this A mu, there could be an interaction between between standard model particles and these particles.
Yes.
So we expect this to be the case in the late time universe. So
yes,
we are already
late
below
time universe.
threshold.
Sorry?
So we are already below this energy threshold.
Yes.
In the present universe.
Yes. Because it's less than larger than 1 TeV. Yes.
Okay. So thanks. So I cannot see more questions. So let's thank Mariam again for his talk. And yes, I think that we have still 10 minutes for discussion. So I know that some speakers wanted to ask more before. For instance, Matteo wanted to ask something to Nick and also to Arman. So please, as there is time, you can ask now. You can take advantage of this extra time that we have. I don't know if Matteo is here actually. Let me check. Okay, he is not here.
Actually,
he asked me actually.
Arman raised the hand.
No, I was clapping. I was clapping.
Okay. Okay.
There is this reaction option which one can clap, but it usually confuses as raising hand. Yeah.
Okay. But can I reply? He asked me. Matteo asked me in the chat, so I can say simply what he asked me. He asked me whether our stringy RVM model can be tested, including all the probes, Planck, Bow, and whatever. I told him not yet. Eventually, this is something that Joanne and I and whomever else is interested, we have to do. The good thing of the stringy RVM is that we can compute the coefficients from the microscopic model of the log H terms and the H square term. So indeed, this should be tested. And dust models, and this is what the remark to all the speakers, because there was an interesting discussion about anisotropies. I believe anisotropies masquerade. I don't believe the tensions are due to anisotropies, but of course, what I believe is not relevant. There was a very interesting papers, but it might be that the dust models sometimes, masquerade themselves. An insufficiency of the dust model can also contribute to tensions, nothing else. That's all I wanted to say.
Okay.
So that's what
I've seen that in your stringy model, you predict at least if I have understood it well, you predict the value in front of h squared to be of the order of 10 to the minus 3. This is
yes, because
right?
it comes from our action kinetic term.
Okay,
Precise,
so
of that order.
this is quite remarkable because this is what we have.
I know.
Say,
I know. Hopefully, one day you would be involved in this analysis, but I want to give you. You have to break for the summer. I would be grateful.
Yeah, Joan, you have a question, a comment?
Yeah, I want to just comment that, as Nick said, in this stringy version of RVM, is very interesting because we can do microscopic calculations. But I want to emphasize that also in the traditional version of the model, we can now perform microscopic calculations. In the presentation by Christian, and also in my presentation yesterday in your session, yeah, it was made clear that we can compute the value of these coefficients nu. And I want to say, I want to advance without telling you exactly what is the result, that we have at right now already computed the 6 adiabatic contribution, and we have some interesting surprises there. So, so we can compute a lot of things right now. So the running vacuum model appeared long ago with some colleagues in a kind of qualitative way, which was related with the renormalization group and so on and so forth. But nowadays we have explicit calculations in which we use a Lagrangian, we use an action, and we compute quantum effects to the vacuum energy. And then we obtain precise predictions. So of course we do not have an exact prediction on this coefficient. We obtain the structure of this coefficient in terms of the various parameters, okay? And then it will depend on the matter content that we have at the end. In particular, we have to add the fermions as well, which nowadays are already computed. So we know the answer too. At some point we will present also these. So we have lots of things, but at the end, of course, there is a comparison with experiment, with observations, and this is, of course, what is physics about. So we can do a lot of things in both languages, in quantum field theoretical language and also in a stringy language. Both of them are very interesting, and I think that that they have interesting news for us in the future.
And if I may add, the important distinguishing feature of the stringy approach is the CPT and Lorentz violation due to the condensate. That leads to leptogenesis. This is what makes this model, in a sense, as I said, it's not CP violation that leads to matter antimatter in the stringy model. It could be CPT as well. That's all. So that's the only feature that, because the quantum field theory, you assume Lorentz invariance, of course, and CPT invariance.
Yeah, of course, sure.
Okay. So
that's the only thing, because of the condensate.
Because of the condensate, yeah.
Because of the condensate.
I have one question for Armand that I haven't had time before to ask. Because in this reconstructed shape of the power spectrum, you find some features at very low case. Do you think that Euclid, for instance, will be able to prove these scales in the near future?
I really think that even using the polarization data, we may rule them out ourselves, to be honest. But then the next step would be that we do the reconstruction, including the polarization. So, I mean, actually, Euclid or Desi, I mean, I think Benjamin was here and he just left. So we worked on some of the approaches to use logical structure data to distinguish some degenerate early universe models, right? So let's say that we have models which have features and the models which they don't have features. It is really difficult. It is really difficult. My expectation is that the information that we can get from the logical structure, because of the galaxy bias, would be very, very difficult to get much information among them. Because, you know, when we do the simulation on the n-body simulation, still things are tricky and complicated. But if and what we observe are galaxies, right? And then we have to consider the halo models and the bias and everything. So I think we would get some information, but I'm not sure that we can break the degeneracies very well. But anyway, that's the next step. Maybe cross-correlating things together, cross-correlating the features which we see, and then using the CMB and logical structure together. But yeah, I mean, that's one of the things that many people, both in Euclid and DESI, they are trying to consider. But let's see. I'm not too hopeful. Let's put it this way.
Thanks. Nico,
yes.
Professor Mavromatos has another question.
Nick, Nick, it's easier. I want actually to ask Arman because of his opinion. As far as I understand, you don't believe in anisotropy yourselves, am I right? Despite the fact that you've done a very good analysis, you still believe it's too early to claim.
I mean,
that's my question.
I think science is a matter of not a matter of
not belief.
So I mean, I wish I could find something. I mean, honestly, the first paper with Subir.
Yes, I'm aware of
that method because I realized that most of the signal that people are finding are because the data is not distributed isotropically on the sky. Yes. So data itself is distributed in like a patch of the sky, and then people are looking for the isotropy in the data, which is not isotropically distributed. So so usually things could get biased slightly towards because of the distribution of the data.
Do you think also could be dust as well playing a role here, masquerading anisotropy, and it's just dust?
I mean, the point is that if we find something, this is at least my approach. If I find something significant, then I try to find a reason,
an explanation.
But
you say it's not significant.
There's a very strong signal. Then I would say that okay, there is nothing much to look for. I mean, okay, something about the CMB is of course very spectacular. What we see in the CMB, I mean, the spherical asymmetry which we see in the CMB, that is something to me that has been a problem. So and I have papers with the Celtic team, Chris Gorski, and then I was not a Planck member, but we found a very small p-value of 0, right? I mean, based on the maps which was made by Planck. So that is something there, but so that is one of the things which still keep me interested about testing the isotropy. And again, I'm not saying about recent Subir analysis, it has a problem. I should read that. I mean, it might be correct, but I'm saying that.
Sure, I mean, it's not a correct.
I agree. One has to be careful not to overinterpret. At least I've seen last 10, 15 years that people find something, and when you do more careful analysis, you realize that okay, something has not been considered. It could be a methodology problem. So I'm very skeptical unless I'm really sure that something is correct.
So you say may not be statistically significant, the evidence.
And that's certainly the case, yes. Many findings are not statistically significant. Yeah.
Thank you.
Okay, now I have one problem for Juan and Nico, if you don't mind. I mean, still you have time, Adria, right?
Yes. Well, okay. Yes. We have 15 minutes.
Okay. So, okay.
Give me 5 minutes at the end, or at least 2. I want you to make a question, but please go on.
Okay, so these models which matter can behave or we have some substances can act like a weird matter, right? Have you ever thought about a kind of a matter which accelerate the universe? Okay, so a kind of a matter, I mean that, to accelerate the universe, we have to inject energy to the universe, right? So what if we have a component which is just like matter, but it's increasing in the universe? Let's say like a matter creation we had in the quasi-steady state universe of Fred Hoyle.
With positive energy density or
positive energy density?
Positive energy density, because with the phantom matter has negative.
No, not phantom matter.
Not phantom matter. Okay. Matter. Well, and by matter you mean what? That the pressure is 0.
Pressure 0.
So ordinary matter from that point of view.
There is a constant creation. So maybe with Benjamin we can send you. We worked on some small model.
Please do that. I'm interested. I'm not. I mean, myself, I was playing with stringy defects, deep particles, which sometimes in the bulk can exert a negative pressure on our brain world, if you assume that our world is a brain. And then this negative pressure would behave like acceleration. So in a sense, but the defects are rather energy rather than matter. You know what I mean? Because there are defects in space-time, and they are massive defects. So they could be. And in fact, some of these defects could also lead to our primordial, with Joan, that we have the primordial gravitational waves. So from that point of view, there is this exotic form But matter alone, I would be very interested. Please send us your work.
This is a crazy idea. This is a crazy idea, which you know, yeah, I will send you two both if you are.
Please,
yeah.
I would be very much interested in this.
But you mean something that produces a repulsion from matter, and
imagine,
even being homogeneous anisotropy without violating homogeneity anisotropy?
So the point is that it's like that everywhere in the universe, continuously matter is created. Okay, so this is the idea goes back to Fred Hoyle idea for the quasi-steady state. We don't need a Big Bang. If we need once creation, why not having creation all the time? So if imagine that you have a matter density into 1 plus z cube, imagine that omega 0 matter itself is increasing now.
Yeah.
Okay. So that basically create a kind of we could explain that we could make acceleration, but we failed in explaining the growth of a structure. So that was where we stuck. But anyway, I can send you. It is one of those, you know.
Well, you may have it in parallel to ordinary matter, which contribute to the growth.
Or we could have it in parallel.
You don't have to have one species.
Right.
The particles, these defects do that. In fact, the defects are in parallel with the stringy defects exert a repulsive force on the brain, and they are in parallel with ordinary matter. But
okay, so. Yeah,
maybe gravitational waves could detect this sort of matter. Maybe there are characteristic signals. I have no idea.
Yeah, I mean, yeah, there would be lots of consequences, I'm sure. You know,
I look forward to seeing this. I wasn't aware of
the ideas that one get interested and it doesn't work, but you know, just not just fun. Yeah.
Sure. Please send us your proposal.
Sure, I will. I think he left, but yeah, we will send.
Yeah, sure.
Okay, Joan, you have a question.
No, I had a question, but I'm not sure if Eoin is around, because the point is that he was mentioning that that he's seen some departure from Freeman-Lemaitre Robertson Walker. I don't know what he means by that actually, because I mean at some point we have some discussion by email, and he mentioned that the running vacuum model, for example, is not FLRW, but this is not true, because if we define FLRW as any model which satisfies Einstein equations up to some terms, for example, some dynamical dark energy terms or whatever, this is still a Freeman-Lemaitre Robertson Walker. So I don't know what he meant by these departures. If he is not around, of course, he cannot answer, but I cannot see that he's around.
No, he's not here.
Okay. So I'm not sure what he means. I wanted to ask him at the end of his talk, but there were so many questions that I didn't have any time.
He sent some references to everybody in the chat, maybe for the supernova. Maybe these your questions are answered there.
No, because, actually,
I think Matteo asked him, and Arman as well sent the paper as well. They are in the chat, so maybe I wasn't aware what deviations they mean. I'm not so sure. Maybe they mean the anisotropy, because Shubir, as you know, claims that there is no cosmological constant because we live in a bubble. So that
he claims this since long ago. But the kind of thing that Eoin is mentioning is related to recent measurements.
Of supernova.
So it's something different. But still, I don't understand what he means by these departures of Freeman-Lemaitre Robertson Walker, because I cannot see that the language is sufficiently precise.
Maybe the isotropies he was claiming. Maybe an anisotropic universe violates the cosmological principle. So that's not Friedman-Robertson Walker in that sense. To me, Friedman-Robertson Walker, even an anisotropic one, I agree with you, Joan. It would be an FLW, right? But
that's right.
Our stringy thing is beyond Einstein, but it's an FLRW.
Still,
so I agree with you, but it's a matter of, I don't know.
I mean, I would agree that there is a departure if some term of, I don't know, some R squared term, but of course R squared cannot be, because it would give short distance effects, or 1 over R, for example, okay?
Yeah.
Things like this. This is an obvious departure from FLRW, but not the kind of thing that we are discussing in many models, in which try to solve these tensions. So I'm not sure what he's.
Maybe they are included in these references, because she was mentioning specifically, as far as I understand, supernova. Only supernova, they say
they issued a recent paper. Actually, he made a lot of propaganda because he sent the paper to many people. I was the one of the receivers of this paper, and then I answered, and I asked some questions, but well, I thought that we would finish the conversation here. Actually, I suggested him to present the results here, actually, and but I didn't have time to discuss with him. So okay, next time perhaps. In any case, I think that the conversations and the discussions were very interesting.
Yeah.
So
Well,
thanks a lot.
anything is interesting on the dark sector we know nothing about. So anything is at play, right?
Yeah. Amazing.
Well, we have one positive remark that unparticles cannot solve the age of attention. That I like very well. That's a really physically interesting result and falsifiable result. So that's good. And that was the only positive result, I think.
Well, positive, it is at least a definite result.
Well, that's what I mean. Positive, a good theory is a falsifiable theory in physics. So
yeah. All right. So it seems that they don't cut off yet. Us.
Probably from experience in our session, 15 minutes, I think they give extra. Or they don't cut off, because yesterday even ourselves we continued, if you remember.
Yeah. So there are still 7 minutes left.
So does anybody has any other questions?
No. Maybe we can stop here.
Actually, I have one quick question to Christian and Joan, actually, on all of you. When you consider, can I ask it? It's a very quick question, or?
Yeah, sure.
Can I go ahead? When you consider, actually, also to, not only Christian, to Xavier as well, to everybody of the group. When you consider the Brans-Dicke, suppose that you make the conformal transformation so as you modified your metric, and the Brans-Dicke gets the Einstein term. In that case, your cosmological constant, this is actually what I had in mind to ask Xavier and Christian, your cosmological constant we get in this redefined metric a quiescence type, because the psi field will be part of the C. There will be no longer a constant. So my question is, if you get different, that's my question. Usually people say, okay, I can perform a field definition going from the Jordan frame to the Einstein frame, and the two things are equivalent. But maybe they are not equivalent.
Well, they are not equivalent.
Yeah, that's exactly my point.
Because the Jordan frame is...
Yeah, we should predefine.
Because you may have anomalies. You may have conformal anomalies that you cannot. When C is not 1/6, you cannot precisely. That's exactly my point. And I think you saw that. That was my question, actually.
The Jordan frame, the starting frame, in principle, is the physical one.
Very good.
Yeah.
And as I said, if you have conformal anomalies, which it is, if psi is not, you may not be able to perform this equivalence. And many people do that. You see, many people in the Higgs inflation, everybody claims that these are equivalent, but your result shows that they are not. That's
they are not. They are not.
But it's good that you show it with measurements. You see, you show it with data. That's
right.
That's the point. Because otherwise you wouldn't have any way to test conformal symmetry, all right? Okay, we know there are scales, but not at this level, not passing between the two frames. Because there is this misconception or folklore that the two frames are equivalent, all right? I mean, I remember when I was young, everybody...
This is a long discussion, discussion.
Of course, this will take us beyond 5 minutes that they are left.
But maybe at the level of cosmological data, if we redefine the Hubble function and the other observables accordingly, taking into account this conformal transformation, maybe we would find the same.
This is my question, but you may, if
at the classical level,
at the classical level, not quantum,
yeah. The problem is when you go to the quantum level,
the fluctuations, because then you quantum fluctuations.
Then you have the anomalies.
Yeah.
And the anomalies cannot just go from one frame to the other and still claim.
And certainly the quantum
two
effects
frames
enter in the data. Quantum effects enter in the data.
Yeah.
All these fluctuations of the metric, all these are entering. You have cutoffs. You have the cutoff. You have in Christian's approach. You have in your group. You in the top. You have quantum effects. So I believe. This is the question actually I asked when I asked you whether the cosmological constant was constant for the Brans-Dicke or not. And it happens to all the theories with the conformal frame.
In any case, in the calculation by Christian and I, this is done in a standard general relativity. I mean, we do not use Brans-Dicke field in that.
No.
We just use a scalar field. I mean, the simplest thing you can imagine. Well, it's simple, but still is not minimally coupled to gravity. So there is a non-trivial calculation to do, as you have seen, just having a look to the formulas. Okay, so yes.
In fact, in string theory, the dilaton, if you assume a non-constant dilaton, you enter in this problem, and that's why the string frame is the natural frame, because that's the frame where the string coupling is the dilaton, is the exponential of the dilaton. So if the dilaton is not constant, you have measurable effects there.
Exactly.
Of course, in our approach, we took the dilaton constant, Joanna. I mean,
yes,
because you don't want to affect the phenomenology of the string, of course, because all the electromagnetic constants, everything else would depend on that field. So.
But if we wouldn't have taken it constant, it would be there, and still we would believe that this Jordan frame is the physical one.
Absolutely. No, I fully agree. That's what I say, because that's the string frame. From the string point of view, I understand it. That's the natural thing. You have strings. Exactly. That's the frame. You define the frame there.
Yeah, we have to use that dilaton there at some point and see.
At some point, after the summer.
After the summer.
I need a break.
Yeah, the equations are very complicated, as it was shown in that appendix in our physics letters B paper.
Absolutely.
Okay.
So thanks a lot to all the speakers and all the participants for the discussions as well. I think that we only have a couple of minutes or so. Yeah.
Just to remind you that tomorrow we have our last CM3 session, okay? And today afternoon you will get the link and the passcode and everything in order that you can connect quickly tomorrow if you want to participate. Tomorrow it will be in the afternoon at 16:30.
Thank you so much, Adria and Juan and everyone. Yeah.
Indeed.
Thanks.
See you tomorrow.
Thank you to you, Arman, and to all the speakers, certainly. Thanks a lot.
Thank you. Bye-bye.
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 Bye-bye. See you tomorrow.
See you tomorrow. Bye-bye.
Bye.